Welcome to my MCAT General Chemistry review video. Now, this is simply part one of a series of MCAT videos. And in this video, I'm going to cover the basics. Things like atoms, molecules, particles, molarity, concentration, solutions, stoichiometry, and gas laws too. We're going to go over the equations, the concepts, and a lot of examples so that you can learn the material well. It's going to be a very detailed video so that you can learn the concepts well. So if you don't have a good foundation in general chemistry and you have to take the MCAT, this video is going to be very helpful for you. So let's go ahead and begin. Let's get started. So let's start our discussion with atoms. According to Dalton's atomic theory, matter is composed of atoms. And within an atom, you have smaller subatomic particles. In the nucleus, you have particles such as protons and neutrons. Protons have positive charges, neutrons are neutral. And outside of the nucleus, you have electrons, which carry negative charges. The mass of a proton and a neutron is almost about 2,000 times more massive than an electron. It's really about 1,800 something, but close to 2,000. Now, the protons and the neutrons together, they're called nucleons. So here we have a helium atom, which has 2 protons and 2 neutrons. So the mass number is 4. And the atomic number is 2. Atoms are electrically neutral. They have no net charge. If you add up the number of protons and electrons, helium has 2 electrons, 2 protons, so the net charge is 0. In an atom, the number of protons and electrons are equal. In an ion, they differ. The number of protons inside a nucleus is always equal to the atomic number. And the number of neutrons is equal to, it's the mass number minus the atomic number. And the number of electrons is equal to the atomic number minus the charge. So let's go over some examples. Let's say if we have aluminum 27. The larger of the two numbers is the mass number. The smaller one, the 13, that's the atomic number. So therefore, the number of protons that we have is 13 protons. The neutrons is 27 minus 13, so we have 14 neutrons in this structure. And the electrons is going to be the atomic number minus the charge. Now, since there's no charge, it's going to be 13 minus 0, so we have 13 electrons. So this is an atom. Within an atom, the number of protons and electrons are identical, and so therefore there's no net charge. The atom is electrically neutral. But now let's say if we have an ion. An ion is basically a particle with a charge. The number of protons is still going to be the atomic number, which is 13. And the number of neutrons is still 27 minus 13, and that's 14. Now the number of electrons is going to be the atomic number, which is 13 minus the charge, which is positive 3. So 13 minus 3, therefore there are 10 electrons in this ion. If you add up the protons and electrons, we have 13 protons and 10 electrons, which have a negative charge. 13 plus negative 10 equals the net charge of positive 3. So just keep in mind, an ion has an unequal number of protons and electrons, but an atom has an equal number of protons and electrons. Let's try another example. Let's say if we have a phosphorus 31 with a minus 3 charge. Go ahead and calculate the number of protons, neutrons, and electrons in this ion. So the atomic number is 15, so there are 15 protons. The number of neutrons is going to be 31 minus 15, and so that's 16 neutrons. And the number of electrons is the atomic number minus the charge, so that's 15 minus negative 3, which is 18. Two negatives will become a positive. So this one has 18 electrons. So now let's talk about the difference between atoms, molecules, elements, and compounds. So let's start with helium. Helium is atomic in nature. A sample of helium is composed only of atoms. But now hydrogen gas is composed of molecules. A molecule is a particle that contains two or more atoms. Those atoms could be identical or they could be different. H2O is considered a molecule because it's a particle that has two or more atoms. Now, H2O is also called a compound. A compound is a substance that has two or more different atoms. But H2 is not a compound because it has only one type of atom. So H2 is called a pure element. So now, what about sodium chloride? Sodium chloride is not considered a molecule. It is considered to be a compound. It's made up of two different atoms, but because it's composed of ions, it is called an ionic compound. In sodium chloride, sodium has a positive charge and chlorine has a negative charge. So helium is considered to be a pure element, and H2 is a pure element, but H2O and NaCl are considered to be compounds. So let's go over a few more examples related to this topic. So let's try this worksheet. So put a check for every substance on the left that is atomic, molecular, if it's a pure element, ionic compound, or molecular compound. So starting with argon. Argon is a noble gas, which is atomic in nature. It's composed of atoms. So argon is atomic. It's not a molecule. A molecule is composed of two or more atoms. It is considered a pure element. It's made up of only elemental argon. And it's not a compound. For it to be a compound, it can't be a pure element. A compound has to have two or more different kinds of atoms. HF is a molecule. It's made up of two or more atoms. It has two atoms, H and F. So it's not atomic. It's not a pure element. It's a compound. But now, what type of compound is hydrofluoric acid? Well, this is going to be a molecular compound. It's a molecule. It doesn't contain full formal charges. So it's not ionic. So now, what about O3, ozone? Is it atomic or molecular? The particle O3 doesn't consist of a single atom, so it's not atomic. It's composed of multiple atoms, so it's a molecule. And it's also a pure element. It only contains one type of atom. So if it's a pure element, then it's not going to be a compound. It doesn't have different types of atoms. Magnesium oxide is not a pure element. It has two different atoms, so it's a compound. And magnesium is a metal, oxygen is a nonmetal. Typically, when you have a metal and a nonmetal, they usually form ionic compounds. So it's not a molecular compound, and it's not considered to be a molecule, and it's not atomic in nature. Zinc is a metal, but it's atomic in nature. Zinc is composed of atoms. And because it's only one type of atom, it's a pure element. It's not a molecule because there are many zinc atoms that are combined into a crystal. So zinc is not really considered a molecule. It's not a compound because we don't have two different elements. Sulfur trioxide is a compound. It's not a pure element. However, it is a molecule. SO3 is not composed of billions and billions of atoms that form a crystal lattice. SO3 is an individual particle with 4 atoms. So it's not atomic, but it's considered to be a molecule. It's made up of molecular particles. Zinc is not really made up of particles. It's basically one chunk of metal, which consists of billions of atoms together. Now, SO3 is not ionic in nature. It's not composed of a metal and a nonmetal. It doesn't have full formal charges. It has partial charges, but not ionic charges, not like +1 and -1, not like that. SO3 is a molecular compound because it's a molecule, and it does have different atoms within it. Ammonium fluoride is not atomic. It doesn't consist of one type of atom, and it's not molecular. Even though it has multiple atoms, it's really an ionic compound. It has charges. Ammonium, NH4, has a plus charge, fluoride has a minus charge, so it's considered to be an ionic compound, even though there's no metal within it. Typically, most ionic compounds consist of a metal and a nonmetal. So if it's an ionic compound, it's not going to be a pure element, and it's not going to be a molecule. Now, I2 is not atomic. It's made up of 2 atoms, so it's a molecule, and it's a pure element because it's made up of only one type of atom, and so therefore it's not a compound. Now, have you ever heard the term allotropes? What do you think an allotrope is? An allotrope is basically a different form of an element. For example, oxygen, elemental oxygen, can exist as O2 or as O3. Both of these substances are elemental oxygen. O2 is the oxygen gas that we breathe in. O3 is actually toxic for us. That's ozone. That's found in the upper atmosphere of our planet. And so these two different forms of oxygen, they have different chemical properties. One is toxic for us, and one is essential for us to survive. Now, another example of an allotrope is found in carbon. Carbon has different forms. Carbon could be in the form of graphite, which contains carbon-carbon double bonds, or it could be in the form of diamond, which contains single carbon-carbon bonds, or it can be in something called Buckminster fullerene, which is basically a ball of 60 carbon atoms. And so carbon could be in any one of these forms. So that's the idea behind an allotrope. It's basically an element in different forms. But those are the most common allotropes that you might encounter, even though there's some other ones. There's some for phosphorus and for other elements as well, but these are the most common types that you should encounter. So now, what is the difference between a pure substance and a mixture? What do you think? So like water, is that considered to be a pure substance, or is that considered to be a mixture? Water is a pure substance. It has a definite composition, and it has distinct chemical properties. So water is always going to have a hydrogen-oxygen ratio of 2:1. In water, you're going to have 2 parts hydrogen, 1 part oxygen. It's always going to be like that. Another example of a pure substance would be like hydrogen gas. That's one type of substance. Or helium. So a pure substance could be a pure element, it could be a compound, it can be a molecular or even an ionic compound. All of these are pure substances. A mixture is a combination of 2 pure substances. So let's say if we were to mix water and sodium chloride, this is considered to be a mixture. Now, a mixture can be separated into smaller components using physical processes. So this salt water solution or mixture, we can separate sodium chloride from water. For example, if you take salt water and you leave it out in the open, let's say you put it in the sun on a dry day, all of the water is going to evaporate. But the sodium chloride, the salt, is going to be left behind. And so we can separate the components of a mixture by using a physical process such as evaporation. A pure substance, however, you can't separate the elements of a pure substance by physical means. So water, I can't separate hydrogen and oxygen by evaporation or some sort of physical process like freezing or melting or boiling or vaporization. The only way for me to break down a pure substance or to separate the elements within a compound, I need to use a chemical process. For example, like electrolysis. In electrolysis, I can separate hydrogen from oxygen. So let's say if I place two inert electrodes or metals in water, and let's say I have a sodium hydroxide solution, I dissolve sodium hydroxide in it. If you were to pass an electric current through that solution, the water in that solution will decompose into hydrogen gas and oxygen gas if you apply an electric current to it. But that's an example of how you can separate the elements in a compound using a chemical process. But to separate the components of a mixture, to separate one substance from another in a mixture, you need to use a physical process. Now, there's two types of mixtures that you need to be familiar with: a homogeneous mixture and a heterogeneous mixture. When you put salt in water, like sodium chloride with H2O, this is going to be a homogeneous mixture. When you put these two together, you're going to have one clear solution. And a homogeneous mixture is one where it's a solution where you have a constant composition. You only can see one visible part. Now, in contrast, let's say if I mix oil and water, these two, they don't mix. Typically, the oil is less dense than water, so typically the oil is going to float on top. And you can see two distinct layers. You can see the organic oil layer on top and the aqueous water layer on the bottom. And so this is an example of a heterogeneous mixture, when you can see two distinct parts. Now what about air? Is air a homogeneous mixture or a heterogeneous mixture? Air is the air that we breathe, which is a mixture of nitrogen gas, oxygen gas, argon. You might have some water vapor and CO2. It's a homogeneous mixture of these gases. We have a uniform composition of gas and air. So now let's talk about isotopes. So what exactly is an isotope? Isotopes are atoms of the same element but with different mass numbers. So let me give an example: carbon-12 and carbon-13. Now, every type of carbon atom has an atomic number of 6. The atomic number identifies the element. However, carbon may have a different mass, but carbon will always have an atomic number of 6. So carbon-12 has 6 protons, and carbon-13 also has 6 protons because the atomic number is 6. Now, carbon-12 has a mass number of 12. So if we want to calculate the neutrons, which is the difference between the mass number and the atomic number, 12 minus 6 is 6, but for the other example on the right, 13 minus 6 is 7. And we can see that these isotopes, they have different mass numbers and also different number of neutrons. However, an isotope is composed of the same element. Both of them are carbon. If the element is not identical, then it's not an isotope. So isotopes, they have identical numbers of protons. The atomic number is the same, but the mass number and the neutron number are different. Some other examples of isotopes involves hydrogen. This you need to know. So this is hydrogen. It has 1 proton, no neutrons. And this is deuterium. Deuterium has 1 proton, 1 neutron. And of course, all of these have 1 electron. The next one is tritium. Tritium has 1 proton. 3 minus 1 is 2, so it has 2 neutrons, and it has 1 electron. It's another isotope of hydrogen. So now let's go into the periodic table. So first we have hydrogen, and below that we have elements such as lithium, sodium, potassium, rubidium. So this is group 1. And Group 1 mostly is composed of metals with the exception of hydrogen, and these are called the alkaline metals, which are very, very reactive. They react with water and they will produce hydrogen gas. Next to it you have the alkaline earth metals, which includes beryllium, magnesium, calcium, strontium, and so forth. Then after that you have the transition metals. Alright, TM for transition metals. And over here you have like elements like boron, aluminum, gallium. This is group 3. Well, group 13 or group 3A. So this is group 1, group 2, group 3A or 13. And then after boron you have like carbon, silicon, germanium. And then after that you have like nitrogen, phosphorus, oxygen, sulfur, selenium, fluorine, chlorine, bromine, iodine. And then here's helium, neon, argon, krypton. So this is group 4A, 5A, 6A, 7A, 8A. Group 8A is the noble gases. They're very stable, and most of them have their octet requirements satisfied. And so the noble gases, they don't really react much. They're very inert. Group 7A is known as the halogens. These are the most reactive of the nonmetals. Group 6A is called the chalcogens, and the representative elements are all the elements except the transition metals. So groups 1, 2, 3A, 4A, 5A, 6A, 7A, 8A are also known as the representative elements. Now, if it's a transition metal or an inner transition metal, which is like over here, I'll put ITM for inner transition metals. These are not considered to be representative elements. This group here is known as the lanthanides. And then below that, you have the actinides. Now, let's talk about valence electrons and charges. Elements that are in the first column, the columns are the groups. So, group 1, which is the first column, which includes all of these elements, they all contain one valence electron. Group 2 elements like beryllium, magnesium, they have 2 valence electrons. Boron, aluminum, those guys have 3 valence electrons. Carbon has 4 valence electrons, nitrogen has 5, oxygen has 6 valence electrons, fluorine has 7, neon has 8 valence electrons, but helium only has 2. So you can tell the number of valence electrons based on the group number. And the valence electrons are the electrons in the outermost energy level. Basically, the electrons in the last shell of the atom. The core electrons are the inner electrons that are like on the inside. The electrons that are not valence electrons are basically core electrons. Now, elements in the first group form charges or ions with positive 1 charges. Elements in the second group, like magnesium, calcium, they form +2 ions, or ions with +2 charges. Aluminum and gallium, they like to form ions with positive 3 charges. This is going to be -3, -2, -1. Elements like silicon and germanium, the charges that they like to have is +2 and +4. They can vary. But these are the main ones you need to know. Group 1, which is +1, Group 2, +2, Group 3A, +3, and then 5A, 6A, 7A. The ions that they form are pretty consistent. Now, on the left side of the periodic table, you have the metals. So let me draw the dividing line. So to the left of that line, you have the metals, and to the right, you have the nonmetals. Metals conduct electricity. They conduct both actually heat and electricity. Nonmetals do not conduct heat and electricity. Metals are shiny, and they have like a luster to it. Nonmetals are like brittle and dull. They lack that shiny luster that a metal has. And metals, they tend to give away electrons, and they form positive charges. Positive charged ions are also known as cations. Nonmetals, on the other hand, they like to acquire electrons, and as they acquire electrons, they will develop a negative charge, and so that's why they form anions, which are ions with negative charges. Nonmetals are usually electronegative because they like to acquire electrons. Metals are electropositive because they like to give away electrons and develop a positive charge. In the middle, you have something known as a metalloid. So like boron, silicon, germanium, arsenic, Te, these elements are considered to be metalloids. A metalloid is an element that is in between a metal and a nonmetal. A metal conducts heat and electricity very, very well. A nonmetal doesn't conduct heat and electricity at all. Metalloids are in between. They can conduct a small amount of electric current. So metalloids are also known as semiconductors. By the way, whenever you increase the temperature of a metal, the electrical conductivity of that metal decreases. But if you were to increase the temperature of a metalloid like silicon or germanium, the conductivity, the electrical conductivity, actually increases with increasing temperature. Now, another thing you need to know about metals. Metals are ductile and malleable. They can be pulled into wires and hammered into sheets. So make sure you are aware of that. So metals are ductile and malleable. Now, there are some other things I do want to mention about the periodic table. So let's say this is boron, carbon, nitrogen, oxygen, sulfur, selenium, phosphorus, fluorine, chlorine. So let's say if you're given 4 elements, carbon, oxygen, sulfur, and fluorine. Which 2 of these 4 elements are most similar in chemical properties? Now, whenever you have 2 elements of the same group, which is the same column, those elements are going to share similar properties. So oxygen and sulfur are going to behave similar to each other. They're going to have similar chemical properties. They both want 2 electrons. Fluorine and chlorine are chemically similar to each other because they both have 7 valence electrons. Oxygen and sulfur, they both have 6 valence electrons, so they're going to behave in a similar chemical way. Now let's go back to isotopes, particularly carbon-12 and carbon-13. Now we said that isotopes, they have the same atomic number and therefore the same number of protons. They're made up of the same element, but they differ in their mass number, and thus they have different number of neutrons. But something else that I want to mention is that isotopes, because they're made up of the same element, carbon, they have the same chemical properties. So they react in a similar chemical way. However, their nuclear properties are different because the structure of the nucleus is different. So isotopes have the same chemical properties but different nuclear properties. So carbon-12 and carbon-13, they will react the same way in a chemical reaction. They will both react with oxygen gas to produce carbon dioxide in a combustion reaction. However, their nuclear activities are different. Carbon-12 is basically stable, but carbon-13 and carbon-14, they decay over time. They can change into a different element, or they can undergo some sort of radioactive decay reaction over a long period of time, of course. So now let's move on and talk about the transition metals. Transition metals like copper, manganese, chromium, you need to know that transition metals have the property of forming complex ions. They can also form colored solutions, and they have multiple oxidation states. So like iron metal has both the +2 and the 3+ oxidation state. Copper has the 1+ or the +1 and +2 oxidation states. Manganese can go up to +7. So as you can see, they have multiple oxidation states, and they form colored solutions. So like a solution of copper sulfate is blue in water. A solution of nickel chloride is light green. And potassium permanganate, well, it really depends on the concentration. If you have a very dilute solution of potassium permanganate, it's going to look pink. But if it's concentrated, it's going to be dark violet, and it can actually look black. Chromium has a range of colors depending on the oxidation state. It could be green, it could be blue, it could be orange. But the important thing that you want to keep in mind is that transition metals, they form colored solutions. So you might get a question that could ask you, out of the following 4 compounds, let's say if you have sodium nitrate, magnesium chloride, let's say chromium sulfate, and aluminum bromide. Which of the following 4 compounds is a colored solution? Well, what you would do is look for the one that contains a transition metal. And since chromium is a transition metal, we expect that chromium sulfate would form a colored solution. Now, another property of transition metals is their ability to form complex ions. For example, silver. Silver has a strong affinity for ammonia. In fact, it reacts with 2 equivalents of ammonia to form this particular complex ion. And the net charge is still a positive 1. Now the Fe3 plus cation also can form a complex ion with thiocyanate, and it forms this iron thiocyanate complex. And the net charge is 2 plus. It's the sum of positive 3 and negative 1. If you add them, you get +2. So what you want to take from this is that transition metal ions can form complex ions in solution. So now, let's move on into bonding. Let's talk about ionic bonds. So what exactly is an ionic bond, and how is it formed? So let's consider sodium chloride, which has an ionic bond. So let's look at sodium. Sodium is an alkali metal found in group 1 of the periodic table, and so sodium has only 1 valence electron. Chlorine, on the other hand, has 7 valence electrons. Now, sodium, which is a metal, it wants to give away the electron that it has. In metals, they like to give away electrons. When sodium loses or gives away the electron to chlorine, sodium is going to have a positive charge, and so it's going to be called a cation. Now chlorine, which gains an electron, it's going to have a negative charge, and so it's called an anion. Now we know that opposites attract. A positive charge is attracted to a negative charge, and that force of attraction, this is called an electrostatic force, and that force is what keeps together the ions within an ionic crystal. And so that ionic bond is due to that electrostatic force of attraction between the positively charged sodium cation and the negatively charged sodium anion. So in an ionic bond, you have a transfer of electrons, and as a result, these ions are formed, and that's what keeps the bond held together. So now let's talk about a covalent bond. What do you think a covalent bond is? We said that an ionic bond involves a transfer of electrons, and a bond is held together by electrostatic force of attraction between opposite charges. But what about a covalent bond? So let's consider 2 hydrogen atoms. Hydrogen is in group 1 of the periodic table, and so it has 1 valence electron. Now when these 2 atoms come together, they're going to turn into a molecule. And so each bond represents 2 electrons. So this line that you see is a covalent bond which contains 2 electrons. And notice that each hydrogen atom donated 1 electron to make that bond that contains 2 electrons. And because they're sharing electrons, this is called a covalent bond. And because they're sharing electrons equally, it's called a nonpolar covalent bond. The electrons are distributed evenly in that bond. So if that's a nonpolar covalent bond, what is a polar covalent bond? So let's consider the interaction between hydrogen and fluorine. Now fluorine has 7 valence electrons and hydrogen has 1. Now fluorine is going to donate 1 electron to form a bond, and hydrogen is going to donate 1 electron. So when you draw the bond between HF, or the molecule, it looks like this. So this is the Lewis structure of hydrofluoric acid. So the 2 electrons that were in this bond, one came from hydrogen and the other came from fluorine, and so it's called a covalent bond. However, the electrons in that bond are not shared equally. Whenever you have an unequal sharing of electrons, you have a polar covalent bond. Fluorine is more electronegative than hydrogen, and so fluorine is going to pull the electrons toward itself. And as a result, fluorine is going to acquire a partial negative charge, and hydrogen is going to be partially positive. Whenever you have a substance where one side is positive and the other side is negative, you have a polarized substance. That's what it means for an object to be polar. Any object that is polar has a dipole moment, and the dipole moment always points towards the negative part of the substance. So HF is a polar molecule. It has a net dipole moment that points towards fluorine, and so since we have this unequal sharing of electrons, we have a polar covalent bond. Now there's another type of bond that you need to be familiar with, and that is called a coordinate covalent bond. In a coordinate covalent bond, one atom donates both electrons in the bond. So let's consider the interaction between, let's say, aluminum chloride and ammonia. When these two interact, the nitrogen atom in ammonia is going to donate both electrons to form the bond between aluminum and nitrogen. And so it's going to look like this. And because nitrogen donated both electrons to form that bond, the bond between aluminum and nitrogen is called a coordinate covalent bond. So in a polar covalent bond and in a nonpolar covalent bond, each atom donates 1 electron to form the bond that has 2 electrons. But in a coordinate covalent bond, 1 atom donates both electrons to form that bond. So now let's talk more about bonds. Let's discuss the single bond, the double bond, and the triple bond. Which of these bonds are the longest? Single bonds are very long, and double bonds are short, but triple bonds are even shorter. So out of these 3, the triple bond is the shortest, and the single bond is the longest. But now, out of these bonds, which one is the strongest? Even though the triple bond is the shortest, it's the strongest of the 3. And the single bond is the weakest. 3 bonds are stronger than 1 bond. Now, a single bond only contains a sigma bond. The double bond has 1 sigma and 1 pi bond. The triple bond has 1 sigma and 2 pi bonds. So, in this molecule, how many sigma and pi bonds are there? let's count the sigma bonds. This is 1, 2, 3, 4. There's 5 sigma bonds. And because we have a double bond, there's at least 1 pi bond. The sigma bond is basically, it's formed through the overlap of atomic orbitals. And the pi bond is basically an unhybridized p orbital. And the overlap of those unhybridized p orbitals forms the pi bond. Now, even though a double bond is stronger than a single bond, a sigma bond is stronger than a pi bond. Now, let's talk about elements and some of their properties. First, let's talk about the diatomic elements, which you need to know. If you hear the word hydrogen gas, it's not simply just H. It's H2. Hydrogen gas is diatomic. It exists as H2. Some other diatomic elements that you need to know are nitrogen gas, oxygen gas, fluorine gas, chlorine gas. Bromine is red, and bromine, it's a liquid. It's not a gas. Chlorine has like a greenish color to it. And iodine is actually a solid. And it has this purple-violet color. Now, out of most of the metals, there's one metal that you need to know that's a liquid, and that's mercury. Mercury is a liquid at room temperature. And phosphorus is in the form of P4 in its natural state. Sulfur forms octagon rings. Sulfur exists as S8. So those are some things that you just want to know if you're ever tested on such information. So now, what is the difference between an intensive property versus an extensive property? An intensive property is the same as an intrinsic property, and an extensive property is the same as an extrinsic property, just so you know. So mass, would you describe mass as an intensive property or an extensive property? What about density? So mass and volume are extensive properties. Density, on the other hand, is an intensive property. For example, the density of aluminum is about 2.7 grams per cubic centimeter. So, regardless if I have a chunk of 50 grams of aluminum or, let's say, 200 grams of aluminum, the density is still going to be the same. So, the density does not depend on the amount or the size of the aluminum sample that I have. If I have 50 grams of aluminum or 200 grams of aluminum, the density will remain the same. And that's why density is an intensive property. An intensive property is one that doesn't depend on the size of the sample. It doesn't depend on how much mass you have. Now, an extensive property is one that depends on the amount of material. So here I have a larger amount of aluminum, so mass is an extensive property. It depends on how much aluminum I have. And the same is true for volume. The more aluminum I have, the more space it's going to take. So mass and volume are extensive properties of matter because they depend on the amount of matter that is present. So we're given the relative percent abundance of 2 isotopes of chlorine. How can we calculate the average atomic mass? The equation that we need, the average atomic mass in AMU, is going to be equal to the mass of the first isotope times the percentage in decimal form plus M2P2. So the mass of the first isotope is about 35, and 77.5% as a decimal is 0.775. Basically, you just need to take 77.5 and divide it by 100. Now, the second isotope has a mass of 37, and the percentage is 0.225. So if you type this in your calculator, you should get 35.45, which is the average atomic mass that is found on a periodic table for chlorine. The average atomic mass of boron is 10.81 based on the isotopes B10 and B11. Calculate the relative percent abundance of isotope B10. So let's use the equation that we used last time, where the average atomic mass is equal to the equation M1P1 plus M2P2. So we know the average, it's 10.81, and the mass of the first isotope is 10, and the mass of the second one is 11. Now, since we're looking for the relative percent abundance of isotope B10, we're going to make P1 equal to X. Now let's think about this. Let's say if P1 is 20%, that means P2 would be 80%. So if P1 is 0.2, P2 is 1 minus 0.2, which is 0.8. So therefore, we could say it's going to be 1 minus X. X plus 1 minus X is 1, which represents 100%. So now at this point, let's go ahead and distribute the 11. So we're going to get 11 times 1, which is 11, and 11 times negative X, which is negative 11X. And now let's go ahead and combine like terms. So 10X plus negative 11X, well, that should equal negative 1X. And next, we're going to subtract both sides by 11. So 10.81 minus 11, that's negative 0.19. And so if we multiply both sides by negative 1, we can see that X is positive 0.19, or basically 19%. So if isotope B10 is 19%, that means B11 is 81%. But the answer that we're looking for is 19%. But let's understand what this means. This means that out of all of the boron atoms that occur naturally on planet Earth, 19% is boron 10. 81% out of all of the boron atoms is boron 11. And notice that the atomic mass, 10.81, is closer to 11 than it is to 10 because we have more of the B11 isotope. We have 81% of it. And so the average atomic mass is going to be closer to the mass of the isotope that has a higher relative percent abundance. So now let's go into units. So you need to be familiar with some units of mass. You need to know that 1 kilogram is equal to 1,000 grams. So these are some common conversions. And for units of length, 1 kilometer is equal to 1,000 meters. And 1 kilometer is also equal to 0.6214 miles. 1 mile is about 5,280 feet. And 1 foot is equal to 12 inches. And 1 inch is about 2.54 centimeters. And 1 meter is 100 centimeters. 1 yard equals 3 feet. And 1 angstrom is about 1 times 10 to the negative 10 meters. Okay, so now let's move on to units of time. You know, 1 minute equals 60 seconds. And in 1 hour, there's 60 minutes. In 1 day, there's 24 hours. And in 1 year, 365 days. So now let's move on into units of volume. 1 liter is equal to 1,000 milliliters. And 1 milliliter is the same as a cubic centimeter. And 1 cubic meter, well, that's equal to 1,000 liters. So let's work on some practice problems. How would you convert 346 grams into kilograms? Feel free to pause the video and try this conversion yourself. So start with what you have, which is 346 grams over 1, and let's convert it into kilograms. So we're going to use the fact that 1 kilogram is equal to 1,000 grams. So since we have the units grams on top, we're going to put the units grams on the bottom, and so kilograms is going to go on top. The number that's next to the kilograms is a 1, and the number that's associated with the grams is 1,000. So as we can see, the units grams cancel, so it's 346 divided by 1,000. If you have numbers on top, you need to multiply, and if it's on the bottom, you got to divide. So 346 divided by 1,000 is the same as 0.346 kilograms. And that's how you can convert from grams into kilograms. Try this one. Go ahead and convert 36 square feet into square yards. So how would you perform that conversion? So let's start with 36 feet squared. Now we need to know the conversion between yards and feet, and it turns out that 1 yard is equal to 3 feet. So we're going to put the units feet on the bottom because we have feet on top, and we're going to put the units yards on top. And the number that's associated with feet is 3, and the number that's next to yards is 1. Now notice that we have a square. So what we're going to do is we're going to square this equation. So 3 squared is 9. 36 divided by 9 is 4. So it's 4 square yards. So now it's your turn. Try this one. 288 cubic inches. And let's convert that into cubic feet. So let's start with what we have. 288 cubic inches over 1. So now, what is the conversion factor between inches and feet? 1 foot is equal to 12 inches. So since we have the units inches on top, we're going to put inches on the bottom and feet on top. So the number that's associated with the inches is 12, and the number in front of feet is 1. And so what we're going to do now is we're going to raise it to the 3rd power. So what we need to do is we need to divide 288 by 12 to the 3rd. So let's clear the page, because when you're taking the MCAT, you can't really use a calculator, so we'll have to do this mentally. So 288 divided by 12 to the 3rd. 288 is 2 times 144, and 12 to the 3rd is the same as 12 times 12 times 12. And 144 is also 12 times 12. So we can cancel these 12s. So what we have left over is 2 over 12. And if we divide it backwards, 12 divided by 2 is 6, so 2 over 12 is 1 over 6. And 1 over 6 is 0.167. And so that's the final answer. So let's try another example. Try this one. Convert 27 meters per second into kilometers per hour. So let's write it as 27 meters over 1 second. And first, let's convert meters into kilometers. We know that there's 1,000 meters per 1 kilometer. So the units meters cancel. So we don't need to change that any further. So now let's convert seconds into minutes. There's 60 seconds in 1 minute, and there's 60 minutes in an hour. And that's all you got to do. So we can see that the units seconds cancel and minutes cancel. So now we just got to do the math. So 27 divided by 1,000 times 60 times 60. And that is equal to 97.2 kilometers per hour. Now, we're really not supposed to use the calculator. So let's see if we can get the same answer without the calculator. So it was 27 times 60 divided by 1,000. So how can we reduce this? Well, 60 is 6 times 10. And so the other 60, we can break into 6 times 10. Now 1,000 is 10 times 10 times 10. So let's cancel 2 of the 10s. So now what we have left over is 27 times 36 divided by 10. So what can we do at this point? What would you do? Let's see. 27 is 9 times 3. And 3 times 36. 36 plus 36 is 72, plus another 36, that's 108. So what we really have is 9 times 108 divided by 10. So now at this point, you can estimate it. You can say, you can round 9 to about 10. I guess you can cancel this. Basically, you're looking for 90% of 108. So what's 90% of 108? Well, 10% of 108 is 10.8. So if 100% is 108, then 90% is 108 minus 10.8. So let's take away 10.8 from 108. 108 minus 10 is 98, and 98 minus the 0.8 would give us 97.2. That's one way in which you can get the answer without using the calculator. But there's other ways too. But sometimes you have to estimate the answer. So let's briefly review the metric system. So we're going to talk about prefixes such as tera, giga, mega, kilo, and then there's centi, milli, micro, nano, and pico. These are the most common ones that you should encounter. So tera is basically 10 to the 12, and giga 10 to the 9. Giga is a billion. Mega stands for a million, or 10 to the 6. Kilo is 1,000, or 10 to the 3rd. Centi, think of a cent, it's 10 to the minus 2. Milli is 10 to the minus 3. Micro, 10 to the negative 6. Nano, 10 to the negative 9. And pico, 10 to the minus 12. So let me help you to see what this means. So let's look at the word giga. So 1 gigameter is equal to 1 times 10 to the 9 meters. So there's always a 1 in front of the prefix. So 1 kilometer is equal to 10 to the 3, or 1,000 meters. 1 nanometer is equal to 1 times 10 to the minus 9 meters. 1 millimeter is equal to 1 times 10 to the minus 3 meters. That's how you can derive the conversion factors from these values. So let's put this information into good use. Let's apply it. So let's say if you have 3.46 times 10 to the minus 3 millimeters, and let's say you wish to convert that into nanometers. How would you do it? The first thing I would do is convert millimeters into meters, and then meters into nanometers. So milli is 10 to the minus 3. That means that 1 millimeter is equal to 1 times 10 to the minus 3 meters. That's one of the conversion factors I'm going to use. The other one is for nanometers. Nano is 10 to the minus 9, so 1 nanometer is 1 times 10 to the minus 9 meters. So now that we have the conversion factors that we need to get the answer, let's go ahead and do it. So let's start with what we have. 3.46 times 10 to the minus 3 millimeters over 1. So let's convert millimeters into meters. So millimeters is going to go on the bottom. So there's 1 times 10 to the minus 3 meters for every millimeter. So the units millimeters cancel. And now let's convert meters into nanometers. So for every 1 times 10 to the negative 9 meters, there's 1 nanometer. And so here's the 1 nanometer, we put it here. And this part went on the bottom. And so the units meters cancel. And now let's see if we can get the answer. So a property of exponents is, let's say if I take this number and move it to the top, the negative 9 will become positive 9. So what I really have is 3.46 times 10 to the minus 3 times another 10 to the negative 3, which is this one. And if I move this to the top, it's going to be times 10 to the 9. So all I really need to do is worry about the exponents. When you multiply bases, you can add the exponents. For example, x squared times x cubed is equal to x to the 5th. 2 plus 3 is 5. So here, if we multiply these values, the base 10 is going to be the same, and I'm allowed to add the exponents. So negative 3 plus negative 3 plus 9. Negative 3 plus negative 3 is negative 6. Negative 6 plus 9 is positive 3. So the final answer is 3.46 times 10 to the 3 nanometers. Try this one. Let's say if we have a 0.046 megawatts, and let's say we want to convert it to centiwatts. How would you do it? So let's find out what conversion factors we need. We know mega is 10 to the 6. Let's convert mega to the base unit watts, and then watts to centiwatts. So 1 megawatt is equal to 1 times 10 to the 6 watts. And 1 centiwatt, centi is 10 to the minus 2, so 1 centiwatt is 1 times 10 to the minus 2 watts. So let's start with the number that we have. 0.046 is the same as 4.6 times 10 to the minus 2. That's what this number is. So if you take the decimal and if you move it 2 spaces to the right, the exponent is going to decrease by 2, so that's how we get negative 2. So I'm going to leave it as 4.6 times 10 to the minus 2 megawatts. Now, because the megawatts is on top, we need to put that unit on the bottom. And so watts is going to go on top. And the number in front of watts is 1 times 10 to the 6, and the number in front of megawatts is a 1. So now, in the next step, we need to convert watts to centiwatts. So since watts is on top again, let's put that on the bottom, and centiwatts is going to go on top. So the number that's in front of watts is 1 times 10 to the minus 2. And the number in front of centiwatts is 1. And so these units will cancel, and those units will cancel. So now what I'm going to do is take the 10 to the negative 2 and move it to the top. So what I now have is 4.6 times 10 to the minus 2 times 10 to the 6 and times 10 to the positive 2. Negative 2 plus 2 is 0. So my final answer is simply 4.6 times 10 to the 6 centiwatts. By the way, some basic formulas that you need to know is the Kelvin temperature equation. Kelvin temperature is equal to the Celsius temperature plus 273.15. But typically, if you just add 273, you should be fine. And the Fahrenheit temperature is 1.8 times the Celsius temperature plus 32. You may need to know that. Now, the density equation, density is equal to mass divided by volume. Now, sometimes it might be easy to know this form of the equation. Mass is density times volume. In this form, you can solve for mass, density, or volume. Just plug in the two variables that you have and simply solve for the missing variable. Go ahead and try this problem. A 7.45 gram rock was dropped into a graduated cylinder containing 24.8 milliliters of water. The volume increased to 26.7. Calculate the density of the rock in grams per milliliter and in kilograms per cubic meter. So the equation for density is D is equal to M over V. And we have the mass of the rock. It's 7.45 grams. Now what we need to find is the density of the rock. So we need the volume. And so since the volume increased from 24.8 to 26.7, that increase or that change in volume represents the volume of the rock. And this is one effective way to calculate the density of an item by water displacement. And so if we take the difference between 26.7 and 24.8, let's do old school subtraction. If we borrow a 1 from the 6, this becomes 5. And we could transfer that 1 to the 7. So 17 minus 8 is 9. And 5 minus 4 is 1. And 2 minus 2 is 0. So it's basically 1.9. So 7.45 divided by 1.9. And that should give us the density. If we use the calculator, 7.45 divided by 1.9 is about 3.92. But now, how can we do this without the calculator? Well, I guess we can resort to long division. So 1.9 divided by 7.45. Actually, before I do that, let's make this easier. If I multiply top and bottom by 10, this is basically 74.5 and 19. So now let's do long division. So how many times does 19 go into 74.5? Well, 19 times, let's see, 19 plus 19 is 38. And if we add another 19 to that, that's 57. And if you add another 19, that's going to be 76. So that's too much. So 19 goes into 74 at least 3 times. And 19 times 3 is 57. And if we subtract 57 from 74, that's going to be 17. So we got 17.5. And what we're going to do is we're going to put a decimal here and see how many times 19 go into 175. Well, we know 19 times 10, if you add a 0, is 190. So if you take away 19 from that, 190 minus 19 is basically 171. So 19 times 9 is 171. And so we have 4 remaining. So I'm just going to put the 4 here because I'm out of space. And let's add a 0. So I'm going to put the 0 there. So how many times does 19 go into 40? Well, 19 go into 40 at least 2 times. And that's going to be 38 with a 2 remaining. And I think at this point this is good enough. And so we can see that the density is about 3.92 grams per milliliter. But we're not done. We need to convert the density of 3.92 grams per milliliter into kilograms per cubic meter. So how can we do this? Well, let's write out the important conversion factors. We know we need to convert grams into kilograms. And we know that 1 kilogram is equal to 1,000 grams. Now, the second thing we need to do, somehow we need to convert milliliters into cubic meters. And we know that 1 milliliter is equal to 1 cubic centimeter. And in addition, 1 meter is 100 centimeters, or 1 centimeter is 1 times 10 to the minus 2 meters. But I like to use the common conversion. So let's start with 3.92 grams per milliliter. And so there's 1 kilogram per 1,000 grams. And so we can see the unit grams cancel. So now let's focus on milliliters. There's 1 cubic centimeter per 1 milliliter. And so this unit, well, actually, I did that wrong. Milliliters should be on top. So always good to make sure that the units cancel. So now milliliters cancel. And then finally, we need to convert centimeters into meters. And there's 100 centimeters per meter. But notice that we have a cube here. It's to the 3rd power. So therefore, we need to raise this to the 3rd power. So our final answer will be in the appropriate unit. It's going to be in kilograms per cubic meter. So now what we got to do is we got to do math. So it's 3.92, and 100 cubed is basically 100 times 100 times another 100. And we have 1,000 on the bottom. So let's cancel some zeros. So these will cancel, and those will cancel, and that will cancel. So basically what we really have is just, we don't have to worry about the ones. So we have 3.92 times 3 zeros. So 1 and 3 zeros is basically 1,000. So what we really have is 3.92 times 1,000. Well, 3 times 1,000 is 3,000, so 3.92 times 1,000 is 3,920. And so that's going to be answer. It's going to be 3,920 kilograms per cubic meter. So whenever you need to go from grams per milliliter, which is density in chemistry, to kilograms per cubic meter, basically what you really need to do is multiply by 1,000. That is the quick way to get the answer. And if you need to go backwards, simply divide by 1,000. So now let's talk about accuracy and precision. So here's a question. The density of iron metal is 7.87. Which of the following students has data that is precise but not accurate? Now, accuracy, it carries the idea of being very close to the accepted value. So the student that is accurate has data that is very close to the accepted value for the density of iron, that is 7.87. Precision is how close your data is with one another. So Mike, his data is accurate because it's close to 7.87, but it's not precise. His data doesn't agree with one another. Now, if you look at Nicole, her data is very precise. Each of her numbers agree with one another. 7.871, 7.873, 7.872, those numbers are very close to each other. So her experiment was precise. And it's also accurate because it's very close to the accepted value. Now, Juliet, her experiment was precise. Her numbers agree with each other, but it's not accurate because she's far off from 7.87. So the answer for this question is Juliet. She has data that is precise but not accurate. Now let's talk about naming compounds. There's two types of compounds, well actually three, but right now we're going to focus on two types of compounds. That is naming molecular compounds or covalent compounds versus ionic compounds. So how would you name these two compounds? MgCl2 and SF6. On the left, MgCl2 is called magnesium chloride. Now, on the right, this is called sulfur hexafluoride. Now, why is it that for the compound on the right, we use the prefix hexa, but for the one on the left, we don't use like a prefix like di? We know di represents 2, hexa represents 6. So why do we use prefixes for SF6 but not for MgCl2? MgCl2 is an ionic compound. It's composed of ions. And typically, if you see a metal and a nonmetal, it's usually an ionic compound. Magnesium is a metal. It's on the left side of the periodic table. And chlorine is a nonmetal because it's on the right side of the periodic table. SF6, on the other hand, is a molecular compound. Notice that it's composed of nonmetals. It's not composed of ions. Sulfur and fluorine are both on the upper right corner of the periodic table, and so they're both nonmetals. Now, for molecular compounds, you're allowed to use prefixes like mono, di, tri, tetra, and so forth. For ionic compounds, you should not use it. So what we're going to do is we're going to start our discussion with molecular compounds. So you need to know that mono represents 1. Di represents 2. Tri represents 3. Tetra represents 4. Penta is for 5. Hexa is 6. Hepta is 7. I wrote 7 for hexa, but I meant to write 6. Hepta is 7. Octa is 8. Nona is 9. And finally, deca represents 10. So now let's put this information to good use. Go ahead and name the following molecular compounds: CO, CO2, SF4, N2O5, and P4O10. So CO, it's not monocarbon monoxide. For the first element, if it has a 1, you don't need the prefix mono, but for the second element you do. So CO is called carbon monoxide. You don't use mono for the first element. CO2 is called carbon dioxide because there's 2 oxygens. Di represents 2. SF4 is sulfur, and tetra is for 4, so sulfur tetrafluoride. And N2O5. So now we need the prefix for the first element because there's 2 nitrogen atoms. So it's going to be dinitrogen, and penta for 5, so pentoxide. And P4O10, that's going to be tetraphosphorus, tetra for 4, and then decoxide or decaoxide, which I ran out of space, but let's see if I can fit it in here. So decoxide or decaoxide, but that's how you would name it. So let's work on some more examples. Write the formulas for the following molecular compounds. So let's say if we have phosphorus, trichloride, and let's see, arsenic, pentabromide, and dinitrogen trioxide. So feel free to pause the video and try these examples. So phosphorus trichloride. Phosphorus is P, chloride is Cl, and there's 3 Cl, so PCl3. Arsenic pentabromide. So arsenic is As, penta means 5, bromide is Br, so AsBr5. Dinitrogen trioxide, that's N2O3. So that's how you can name and write the formulas of molecular compounds. Very easy. So before we begin reviewing how to write formulas for ionic compounds and naming ionic compounds, let's review the monoatomic ions and the polyatomic ions. So in the first column, we have hydrogen, which has a +1 charge, lithium, which also has a +1 charge, sodium and potassium. All of the group 1 metals, including hydrogen, which is not a metal, have a +1 charge. In the second column, we have group 2 elements like beryllium, magnesium, calcium. These two, they form 2+ charges. And then in group 3A, you have elements like aluminum and gallium. And typically, they form charges with, they have an oxidation state of +3. And then you have elements like nitrogen, phosphorus, oxygen, sulfur, fluorine, chlorine, bromine, iodine. Nitrogen typically has a -3 charge as an anion, and for phosphorus it's -3. Now for oxygen, it's going to be -2, and fluorine -1, and the rest of the halogens is going to have a -1 charge. So these are the monoatomic ions. Now, when you're dealing with ionic compounds, the first element would be like lithium or sodium. It's just going to be the name of that element. But the anions, they're going to have the end in "ide." So when you hear the word chloride, it's a monoatomic ion called Cl-. Oxide is also monoatomic. It's O-2. So N-3 is called nitride. P-3 is phosphide. This is sulfide, iodide, bromide, chloride, fluoride. So if it ends in IDE, typically it's a monoatomic anion. So right now we're going to go over polyatomic ions, and I might include some monoatomic ions for the sake of comparison. So what do you think the names are for these three ions? S-2, well, this is called sulfide, and SO3 2- is sulfite, and SO4 2- is called sulfate. Now, notice that 8 has one more oxygen than ite, and all of the charges are the same, but that won't always be the case. Consider these three. What do you think the names are for these three ions? So N3- is known as nitride. It has an IDE ending. It's a monoatomic ion. And here we have a polyatomic ion called nitrite. And this one is a nitrate. So notice that 8 has one more oxygen. But in this case, the charges are not identical. Nitride has a charge of -3, but nitrite and nitrate has a charge of -1. So what about these three? What do you think the names for these ions are? So P3- is phosphide. PO3 is known as phosphite. And PO4 3- is called phosphate. By the way, what do you think H PO4 2- is called? And what about H2 PO4-? So H PO4 2- is hydrogen phosphate or monohydrogen phosphate. H2 PO4- is dihydrogen phosphate. Try these 5. See if you can name them. So the first one is called chloride. The second one is called hypochlorite. And the third one is simply called chlorite, that's ClO2-. And ClO3-, this is called chlorate. As you can see, 8 has one more oxygen than ite. And then the last one is called perchlorate. Now, the trends for the other halogens like bromine and iodine, they follow the same pattern. So, to illustrate, try these 5 compounds: Br-, Bro-. Go ahead and name these ions. So, Br- is called bromide, and Bro- is hypobromite, and for Bro2-, this is simply called bromite, and Bro3-, that's bromate, and the last one is called perbromate. Now, here are some other ones that you need to know. So we have OH-, CN-, C2H3O2 minus, and MnO4 minus, CrO4 2 minus, and Cr2O7 2 minus. So OH minus is called hydroxide, and Cn minus is cyanide. C2H3O2 minus, this is called acetate, and here we have permanganate, and this is called chromate, and this is dichromate. Try these. CO3 2 minus, HCO3 minus, C2O2 2 minus, O2 minus, O minus 1, and O2 minus 1. So this is called carbonate. And here we have, you can call it bicarbonate. It's also monohydrogen carbonate. This is called oxalate. That's C2O2 2 minus. And whenever oxygen has a -2 charge or oxidation state, it's called oxide. If it has a -1 oxidation state, it's called peroxide. Sometimes you might see it like this. If you see O2 2 minus, this is also referred to as peroxide. And O2 with a -1 charge, this is superoxide. O-1 is really in this form. The two oxygens really should be together. It's just that the oxidation state for each individual oxygen is -1 in peroxide. For oxide, the oxidation state is -2. For superoxide, each oxygen has an oxidation state of -0.5. So I want to make sure I clarified what I just went over. So whenever you see the word oxide, that means that each oxygen has a charge of -2. So some examples of compounds that have the word oxide is Na2O, this is sodium oxide, and PbO2, that's lead 4 oxide. If you see the word peroxide, typically there's going to be two oxygens that are together, and it's going to exist as O2 with a -2 charge. But each oxygen has an oxidation state of -1 if you divide -2 by 2. So you might see peroxide in the form of H2O2, this is hydrogen peroxide. Or if you see K2O2, that's potassium peroxide. Now granted, this could be reduced to KO, which would still be called potassium peroxide, but typically it would exist as a diatomic oxygen anion. Now, superoxide also exists as a diatomic anion, but the net charge is -1 for the two oxygen atoms. And so individually, each oxygen has an oxidation state of -0.5. So an example of a superoxide compound would be like NaO2. This is called sodium superoxide. Now let's review some ions, particularly metal ions with multiple oxidation states. Most of these will be transition metal ions. So copper has two common forms. That's the copper +1 cation and the copper 2+ cation. Iron also has two forms. It has a +2 and a +3 oxidation state. And chromium also has multiple forms. Two common forms are the Cr+2 ion and +3 ion. Now in chromate, the oxidation state is +6. Now lead is not a transition metal, but it does have variable or multiple oxidation states. The most common are the +2 and +4 oxidation states. And the same is true for tin, which is found in the same column as lead. It has the +2 and +4 oxidation state. And for cobalt, it's +2 and +3. Now there's some transition metals that they have a common oxidation state. They don't really have multiple oxidation states. Like silver, 99% of the time silver is going to be in the +1 oxidation state. Now it can form the +2 and +3 oxidation state, but those are very rare and unstable. So if you're dealing with silver, 99% of the time it's going to be the +1 oxidation state. Now granted, there might be some unusual exceptions, but for the most part silver is +1. Zinc, 99% of the time it's going to be +2. I've never seen a zinc +3 oxidation state or +1. Nickel. Now nickel does have a +3 oxidation state, but it's unstable. So 95% of the time it's going to be +2, unless specified otherwise. Same thing for cadmium. It's like zinc. It's going to have that +2 oxidation state. So now let's spend some time writing the formulas for ionic compounds. So let's start with sodium fluoride. So the first thing we want to do is identify the charges of these elements. Sodium, which is found in group 1 of the periodic table, has a +1 charge. And fluoride has a -1 charge. Whenever the charges are the same, even though they may be opposite in sign, you can simply put them together. This is just going to be NaF. So that is the formula for sodium fluoride. So another example, let's say if we have calcium oxide. Calcium has a 2+ charge, and oxygen has a -2 charge. So notice that the charges are the same, so we can simply write them together. It's just going to be CaO. So what about this one? Let's say if we have aluminum phosphate. Well, aluminum has a +3 charge, and for phosphate, we know that the charge is -3, or 3-. And so since the charges are the same, we can simply write them together. So it's going to be AlPO4. Now, what if the charges are different? So let's say if we have the compound lithium sulfide. How would you name it? Or how would you write the formula? Lithium has a +1 charge, and sulfide has a -2 charge. So you could use the crisscross method, where the 1 is going to go there, the 2 is going to go there. So it's going to be Li2S1, but we don't have to write the 1, so it's Li2S. Here, go ahead and try another example. Let's say if we have calcium bromide, how would you write the ionic compound, or the formula for the ionic compound for this one? So calcium has a 2+ charge, and bromide has a -1 charge. And so using that same technique, it's going to be Ca1Br2. And what about this one? Let's say if you have aluminum. So if we have aluminum chloride, how would you write the formula for the ionic compound? So aluminum is found in group 3A of the periodic table, so it's going to have a +3 charge. And the halogens typically have a -1 charge, so if we use this technique, it's going to be Al1Cl3. But you don't need to write the 1. So go ahead and try this one. Magnesium phosphate. So magnesium has a 2+ charge. It's an alkaline earth metal. It's found in group 2 of the periodic table. And phosphate is a polyatomic ion, and you should just have the structure or the formula committed to memory. So if we use the same technique, it's going to be Mg3PO42. If you have multiple polyatomic ions, you need to enclose it within a parentheses. Now, what about this one? Iron 3 sulfide. And let's also try iron 2 sulfide. So, if you have an ionic compound with a Roman numeral, you need to know the Roman numeral represents the charge. So, in this compound, the iron atom has a charge of +3, and for sulfide, it has a charge of -2. So, using this technique, it's going to be Fe2S3. Now, for the next one, iron has a charge of +2, and sulfur has a charge of -2. So because the charges are the same, we can simply write them together. And so it's just going to be FeS. So now, let's approach this from the opposite viewpoint. Let's say if we wish to name the compound SrBr2. How can we do that? Now, the first thing you need to take into account is, should you use Roman numerals? Now, if the metal atom is like a representative element, like in group 1, group 2, or group 3, where it doesn't have a multiple oxidation state, you do not need to use a Roman numeral. However, for elements that do have multiple oxidation states like copper, iron, lead, tin, cobalt, and the ones that we've listed before, chromium, for those you do need to use a Roman numeral. Now, since strontium typically has a +2 charge, we don't need to use a Roman numeral, so we can simply say strontium, which is the name of the first element, and then the second element, we're not going to say bromine, we're going to say bromide. We're going to add the end in IDE. And that's all you need to do to name this particular ionic compound. So let's try another example. Let's say if we wanted to name Al2SO43. So aluminum doesn't really have multiple oxidation states. It has predominantly one oxidation state, which is the +3 oxidation state. So we don't need to use a Roman numeral. So all we need to do is say aluminum, the name of the first element, and for the second part, it's a polyatomic ion, so we just need to say the name of that polyatomic ion, which is sulfate. So this is called aluminum sulfate. Try these two, CuCl and CuCl2. So you know copper is a transition metal with multiple oxidation states, so here we need to use the Roman numeral. So we'll need to figure out the charge on copper. So if we write an equation, Cu plus Cl, it equals to the net charge of 0. If there's no number here, like a -2, -1, the net charge of the entire compound is 0. Now we know that chlorine has a charge of -1, and since we're solving for copper, we're going to replace it with x. So x plus -1 is equal to 0. If we add 1 to both sides, x equals +1. So copper has a +1 charge. So when we name it, it's going to be copper 1 chloride, since it has a +1 oxidation state. Now for the next one, CuCl2, let's solve for the oxidation state of copper. And so there's 2 chlorine atoms. So it's going to be 2 times -1, which is -2, and if we add 2 to both sides, copper is going to have a +2 oxidation state. And so it's going to be called copper 2 chloride. Oxidation state and the charge, for the most part, they're about the same. For the sake of practice, go ahead and try to name PbO and PbO2. So let's find the oxidation state of lead. So if we write an equation, Pb plus O is equal to 0. And oxygen typically has a charge of -2, which means that lead has a +2 charge. So when we name it, it's going to be lead 2 oxide. Now for the next one, it's going to be Pb plus 2 oxygen atoms, which equals a charge of 0. So each oxygen atom has a charge of -2. 2 times -2 is -4. If we add 4 to both sides, the charge on Pb is +4. So this compound is called lead 4 oxide. Now, if you're not familiar with the Roman numeral system, just to review, this stands for 1, this is 2, this is 3. If you have an I in front of the V, that's 4. V represents 5. And an I that comes after the V is like 5 plus 1. This is 6. And 2 I's after the V, 5 plus 2, this is 7. So just so you can know what these symbols mean. Now let's talk about some rules for naming acids. Let's say if you have an ion that has the suffix IDE, when you name the acid, it's going to have the prefix hydro and the suffix IC. Now for the suffix ite, it's going to convert into the suffix is for the acid. And the suffix ate is going to convert to the suffix ic. So let me show you what I mean. So let's say if we have the monatomic ion sulfide, which is S minus 2. Well, the acid is going to have the formula H2S. Hydrogen has a charge of 1, so if the charge is negative 2, it needs to bind with 2 hydrogen atoms. So we said ide becomes hydro plus IC. It turns out that the name of H2S, it's called hydro sulfuric acid. So here's the prefix hydro, here's the suffix ic, so hydrosulfuric acid. So let's look at another example. SO3 2- is known as sulfite. And we said that if you have the suffix ite, when naming the acid, it's going to have the suffix is. And there's a negative 2 charge, so the acid is going to have the formula H2SO3. And so this is called sulfurous acid. So now what about SO4 2-. We know this is called sulfate. So the acid is going to have the formula H2SO4. And if we have the suffix ate, we know we have to replace it with the suffix ite, or ic. So H2SO4 is called sulfuric acid. Now what about these 5 compounds? HCl, HClO, HClO2, HClO3, and HClO4. How can we name these acids? Well, Cl- is chloride, and whenever you have the suffix IDE, you have to replace it with the prefix hydro and the suffix IC. So HCl is called hydrochloric acid. HClO, ClO- is hypochlorite. We need to replace the ite with is, so this is going to be hypochlorous acid. And here's the ic part and the hydro for that one. Now what about HClO2? So ClO2 is called chlorite. We have to replace the ite with is, so this is going to be chlorous acid. Now how about HClO3? ClO3- comes from chlorate. So we got to replace the ate with ic, so it's going to be chloric acid. And finally, HClO4, which comes from perchlorate. So it's going to be perchloric acid. So now, sometimes you might be given the name of the acid and you need to be able to write the formula. So try these. Nitric acid and nitrous acid. So nitric acid comes from the word nitrate, which is NO3 with a -1 charge. So because it has a -1 charge, we simply need to add one hydrogen ion to it. So the name of nitric acid, or the formula for nitric acid, is going to be HNO3. Now nitrous acid, is associated with ice, so it comes from the polyatomic ion nitrite, which is NO2-, and the charge is -1, so we'll need to add only one hydrogen to it. So nitrous acid has the formula HNO2. So let's try some more examples. Write the formula for phosphoric acid and phosphorus acid. So phosphoric acid comes from the polyatomic ion phosphate, and so that is PO4 3-. So because we have a -3 charge, we need to add 3 hydrogens to it. And so the name of phosphoric acid, or the formula for it, is going to be H3PO4. Now phosphorus acid comes from the polyatomic ion phosphite. Now the charge is still -3, so we still have to add 3 hydrogen ions to it. And so the formula for phosphorus acid is H3PO3. Now what about hydrophosphoric acid? Now if you see the word hydro, that means it comes from a monoatomic ion as opposed to a polyatomic ion. So it comes from phosphide, which is P with a -3 charge, and we have to add 3 hydrogens to it. And so the formula is going to be H3P. That's hydrophosphoric acid. Try these. Hydrobromic acid, bromic acid, carbonic acid, and finally acetic acid. So whenever you see the word hydro, that means we have a monoatomic ion, in this case bromide, and it has a -1 charge, so we need to add 1 hydrogen to it. So the formula for the acid is going to be HBr. Now for bromic acid, it comes from the polyatomic ion bromate, which is BrO3 with a -1 charge, and so we need to add 1 hydrogen to it, so it's going to be HBrO3. Carbonic acid comes from the polyatomic ion carbonate, which has a -2 charge, so therefore we have to add 2 hydrogens to it. So the formula for carbonic acid is H2CO3. And for acetic acid, it comes from the polyatomic ion acetate, C2H3O2-. And because it has a -1 charge, if you want to write the formula for acetic acid, we need to add 1 hydrogen to it. So it's going to be HC2H3O2. For organic acids, notice that the hydrogens are separated. The hydrogen that's in the front, that's the acidic hydrogen. The hydrogens in the middle are not acidic. The next thing that we need to talk about is the mole. What exactly is a mole? A mole is a quantity. When you hear the word a dozen, what do you think of? A dozen simply represents the value of 12. So if you have a dozen eggs, that means you have 12 eggs. If you have a dozen calculators, it means you have 12 calculators. Well, just as a dozen equals 12, a mole equals a very large number, 6 times 10 to the 23. So if you have a mole of books, you have 6 times 10 to the 23 books. If you have a mole of papers, you have that many papers, 6 times 10 to the 23 papers. And that's really what a mole is. It's simply a large quantity. It turns out also that another conversion factor that you may need to know is this one. 1 gram is equal to 6.022 times 10 to the 23 atomic mass units. The number 6 times 10 to the 23 represents Avogadro's number. So if you need to convert from like moles to atoms, you can use this conversion. Or if you want to convert from like moles to particles, moles to molecules or ions, you can use that. If you need to convert from grams to atomic mass unit, you can use this, but we're not going to use it anytime soon. but you can jot this down in your list of notes. Now the next thing we need to talk about is the molar mass. When you hear the word molar mass, what do you think of? It has the idea of, it connects moles with mass. The molar mass is simply the number of grams per 1 mole of substance. So let's take carbon for example. If you look at the periodic table, carbon has an atomic weight of 12.01 AMU. It's also called atomic weight because carbon is composed of atoms. Now, when you hear the word molar mass, atomic weight, formula weight, molecular weight, you can find it the same way. Basically, you need to just go to the periodic table and look at the mass number. So the molar mass, or the atomic weight of carbon, is 12.01. So what this means is that 1 mole of carbon has a mass of 12.01 grams. Or you can say the molar mass is simply 12.01 grams per mole, or per 1 mole. And that's the idea behind the molar mass. It's the number of grams per 1 mole of substance. Let's try an example. Let's calculate the molar mass of CH4. Now, CH4 is a molecule. It's composed of multiple atoms. So the molar mass is also known as the molecular weight, or the weight of a molecule. And if you don't have the periodic table, go to Google Images and you could find it and print one. And you'll have it handy. Now, carbon has a molar mass, or an atomic weight, of 12.01, but we're going to round it to 12 since we're dealing with the MCAT, and we're going to try to avoid using calculators. Now, there's 4 hydrogen atoms, each with an atomic mass of 1.008, so we'll say it's about 1. And so the molar mass for CH4 is about 16, or 16 grams per mole. Keep this in mind, that what this means is that 1 mole of methane, CH4, has a mass of 16 grams. So you might need this information when you need to convert from grams to moles, or vice versa. Try this one. Go ahead and calculate the molar mass of magnesium chloride. Now, magnesium chloride is a compound. CH4 is a compound too. It's composed of different atoms. But this is particularly an ionic compound because magnesium is a metal, chlorine is a nonmetal. So the molar mass of MgCl2 can also be described as the formula weight, or the weight of an ionic compound. Now, magnesium has an atomic mass of 24.3, and for chlorine it's about 35.45. And so we're going to multiply this by 2 because there's 2 chlorine atoms. Now, 2 times 35 is 70, and 2 times 45 is 90. So 0.45 times 2 is 0.9, so this is going to be 70.9. And if we add these two together, 70.9 plus 24.3, 9 plus 3 is 12. Carry the 1 over. 4 and 1 is 5. 7 and 2 is 9. So the molar mass is 95.2 grams per mole, or 1 mole of MgCl2 is equal to a mass of 95.2 grams of MgCl2. So now we're going to spend some time doing some conversions. So let's start with grams to moles. How would you convert 36 grams of carbon atoms into moles of carbon? So what you need to do is start with what you have. We have 36 grams of carbon, and we're going to put that over 1. Now, because we have the units grams of carbon on the top left, we need to put grams of carbon on the bottom right. Now, we need the molar mass, or the atomic weight of carbon, from the periodic table, and that's going to be our conversion factor. So the atomic weight of carbon is 12. That means that 1 mole of carbon is equal to 12 grams of carbon. So notice that the 12 is associated with the grams of carbon. So let's put that here, and that's equal to 1 mole of carbon, so let's put that on top. And notice that the units grams of carbon cancel. And so all we need to do is divide 36 by 12, which is 3. Now let's think about what this means. So 36 grams of carbon equals 3 moles. Well, if 1 mole of carbon is 12 grams, that means 2 moles of carbon must be 24 grams of carbon. Therefore, we can see that 3 moles of carbon equals 36 grams of carbon. So therefore, 4 moles of carbon will equal 48, and it's going to keep increasing by 12. And so hopefully this helps you to understand the relationship between grams of carbon and moles of carbon better. It's always going to have a ratio of 1 to 12, since the molar mass is 12. So now it's your turn. Convert 88 grams of carbon dioxide into moles. So the first thing I would do is find the molar mass of carbon dioxide. Whenever you want to convert from grams to moles or moles to grams, you need to find the molar mass. So the molar mass for carbon is 12, and for oxygen it's going to be 16, but there's 2 of them, so let's multiply that by 2. Now 2 times 16 is 32, and 32 plus 12, that's 44. So we have 44 grams per mole. So what this means is that 1 mole of carbon dioxide is equal to 44 grams of CO2. So that's our conversion factor. That's going to help us to convert from grams to moles. So now let's start with the grams of carbon dioxide. So we have 88 grams of CO2 over 1. And let's convert it to moles. So because we have grams on the top left, we need grams on the bottom right. So we're going to put 44 grams of CO2 on the bottom and 1 mole of CO2 on top. So these will cancel. 88 divided by 44 is 22, since 8 divided by 4 is 2. So the answer is 22 moles of CO2. Try this one. Convert 11 grams of sodium fluoride into moles. So the molar mass of sodium fluoride, well, the atomic mass for Na, or sodium, that's 23, and for fluorine, that's about 19. So 19 plus 23, that's 42 grams per mole. So let's start with 11 grams of sodium fluoride. So there are 42 grams of sodium fluoride per 1 mole of sodium fluoride. And so the units, grams, will cancel. And so now we got to figure out what 11 divided by 42 is. And whatever that is, that's going to be the answer in moles. So 11 over 42, how can we reduce it? Now we know that 11 over 44 is about 1/4, which is 0.25. So because the denominator is smaller than 44, because 42 is less than 44, if you have a smaller denominator, that means the value of the fraction is going to be larger. So this should be a little bit more than 0.25. So it's probably going to be like between 0.25 and 0.3. So if you have a multiple choice test, you can estimate your answer. But let's actually get the right answer for this. And let's check it with the calculator. So now let's practice our long division skills. So 11 over 42, that's the same as this expression here. Now 42 doesn't go into 11, so we need to add a 0. So we're going to treat 11.0 as if it's 110. And so now we need to add a decimal since 42 doesn't go into 11. So how many times does 42 go into 110? Well, let's make a list. We have 42. If we add 42 to 42, it's 84. And if we add 42 to 84, it's 126, which is too much. So 42 goes into 110 at least 2 times, because 42 times 2 is that's 84. Now, if we subtract 110 from 84, it's really supposed to be a decimal point here, but 110 minus 84, that's going to be 26. Now let's add a 0. So how many times does 42 go into 260? Well, let's add it a few more times. So 126 plus 42, that's 168. And if we add another 42 to that, that's 210. And if we add another one, that's going to be 252. And if we add 42 to that, that's 294, which is too much. So this is what we need. To get to 252, we need to add 42 to itself at least 6 times. 1, 2, 3, 4, 5, 6. So what that means is that 42 times 6 is 252. And 260 minus 252, well, that's about 8. And if we add another 0, 42 goes into 80 at least one time, because 2 times is too much. 84 is greater than 80, so it goes into at least once. Now at this point we can stop. 0.261 is good enough. So now let's see how close we are to the actual answer. So if you take 11 and divide it by 42, if you type that in your calculator, the answer that you should get is 0.2619047. But 0.261 or just simply 0.26, that's enough to select the right answer from a list of other answers. So now let's try another example. But this time, instead of converting from grams to moles, we're going to convert from moles to grams. So let's say if you have 3.5 moles of sulfur dioxide, how can you convert that into grams? Go ahead and try that. So first, let's find the molar mass of sulfur dioxide. Sulfur is about 32, and oxygen has an atomic mass of 16. 2 times 16 is 32. 32 plus 32 is 64. So now let's start with moles. So we have 3.5 moles of SO2. Now, if the molar mass is 64, what that means is that 1 mole of SO2 has a mass of 64 grams. And that's going to be our conversion factor. So since we have moles on top, we need to put moles on the bottom. So we're going to put 1 mole of SO2 on the bottom. And then the other part of the conversion factor, we're going to write it on top. So now we can see that moles of SO2 will cancel. And so the answer is 3.5 times 64. So let's multiply those two numbers. 3.5 times 64. How would you do it? Well, here's one way you can see it. 3.5 is basically 3 plus a half times 64. 64 times 3, that's 192. And half of 64, that's 32. So when you add these numbers, you should get 224. And so that's how many grams of sulfur dioxide are in 3.5 moles of SO2. Try this one. Convert 4.1 moles of H2S, which is called, what's the name of H2S? H2S is hydrosulfuric acid. Convert this into grams. So let's find the molar mass of H2S first. So hydrogen has a molar mass of 1, but there's 2 of them, so we're going to multiply that by 2. And for sulfur it's 32, so the molar mass is 34 grams per mole, or 1 mole of H2S has a mass of 34 grams. So starting with the moles, let's convert it to grams using our conversion factor, which is the molar mass. So 1 mole of H2S has a mass of 34 grams. So the units, moles of H2S, cancel. So now we got to figure out what 4.1 times 34 is. So let's multiply 4.1 by 34. So 4.1 is the same as 4 plus 0.1 times 34. Now, so what's 4 times 34? Well, if we double 34, that's 68. And if you double 68, that's 136. When you double something twice, it's basically the same as multiplying by 4. Or you could do it this way. 4 times 34 is the same as 4 times 30, which if 4 times 3 is 12, 4 times 30 is 120. And 4 times 4 is 16. 120 plus 16, that's 136. And when we multiply 0.1 times 34, that's going to be 3.4. you simply move the decimal 1 unit to the left. And 136 plus 3.4, that's 139.4. Now we can also multiply it this way. 34 times 4.1. So 1 times 4 is 4, and 1 times 3 is 3. So we need to add a 0, and then 4 times 4, that's 16. Carry the 1 over, and then 4 times 3 is 12, plus 1, well, that's 13. And so if we add it, this is going to be 4 and 0 is 4, 3 and 6 is 9, and then 3 and 1. We have one decimal point here, so we need to put that here. So this is going to be 139.4. Try this one. Let's say if we have 3.8 moles of ethane, C2H6, and if we wish to convert it to molecules of ethane, C2H6 is a molecule. It's composed of multiple atoms. How can we do so? Now, keep in mind, Avogadro's number, 1 mole is equal to 6.022 times 10 to the 23, but we're just going to round that and say that's 6 times 10 to the 23. So 1 mole of ethane, C2H6, because that's a molecule, it's equal to 6 times 10 to the 23 ethane molecules, or just we'll write molecules. So let's use that as a conversion factor. So we have 3.8 moles of C2H6. So we need to put moles on the bottom so that it will cancel. And then we're going to put the number of molecules on top. So this is telling us that we need to multiply. These two units cancel, so we got to figure out what 3.8 times 6 times 10 to the 23 is. The first thing we need to worry about is these two numbers. Let's ignore the 10 to the 23. Let's find out what 3.8 times 6 is. So 3.8 is the same as 3 plus 0.8. And if we distribute 6 times 3, well, that's about 18. And 0.8 times 6. If 6 times 8 is 48, then something that's less than 8, 0.8 times 6 must be 4.8. And so 18 plus 4.8 is 22.8. You want to get to a point where you can do this in your head, because it's going to save you time. And so what we now have is 22.8 times 10 to the 23rd. Now what we need to do is move the decimal 1 unit to the left. If we do that, what's going to be the effect on the 23? Is it going to go up to 24, or is it going to go down to 22? If you move the decimal to the left, the exponent should increase. This is going to be 2.28 times 10 to the 24, which is the answer. But let's understand why. So let's start with 22.8 times 10 to the 23. And let's focus on the number 22.8. 22.8 is the same as 2.28 times 10. And we still have the 10 to the 23, which I'm going to bring down. And 10 is basically 10 to the first power. Now, whenever you multiply two numbers that have a common base, you are allowed to add the exponents. For example, x cubed times x to the 8, we simply write 1x, and then we are allowed to add the exponents. 3 plus 8 is 11. So 1 plus 23 is 24, so that's why the answer is 2.28 times 10 to the 24. So whenever you move the decimal 1 unit to the left, the exponent is going to go up. And if you move the decimal 1 unit to the right, the exponent will go down. Somehow you may need to come up with a system to remember that, or you could simply use the technique that we've demonstrated, or that we just went over here. So now let's say if we started with 3.8 moles of ethane again, but this time instead of converting it to molecules of ethane, let's say we want to find the number of atoms of hydrogen. How can we do it? So first, let's start with 3.8 moles of ethane. And we need to convert it to molecules using the same process that we used before. And so 1 mole of ethane contains 6 times 10 to the 23 molecules of ethane. Now we need another conversion factor. At this point, we need to convert molecules into atoms of hydrogen. And notice that 1 molecule of C2H6 contains 6 atoms of hydrogen. And so that's what we can use for our next conversion factor. So 1 molecule of C2H6 equals 6 atoms of hydrogen. So these units will cancel, and those units will cancel. Now, our previous answer was, we know that if we multiply these two numbers, it's going to give us 2.28 times 10 to the 24. And we simply have to multiply that number by 6. So what is 2.28 times 10 to the 24 multiplied by 6? So let's multiply it by hand. 2.28 times 6. 8 times 6 is 48. And 2 times 6 is 12. Plus 4, that's 6. Or 16. And then carry the 1. 2 times 12 is... 2 times 6 is 12. Plus 1 is 13. So we should get 13.68. So this is 13.68 times 10 to the 24. And if we move the decimal 1 unit to the right, this is going to increase by 1. So the answer is 1.368 times 10 to the 25. And you could check that with the calculator to make sure that it's correct. And it is. So that's how many atoms of hydrogen are found in 3.8 moles of ethane, C2H6. Now, let's say if you have 4.3 moles of aluminum chloride. How can we convert it to formula units of aluminum chloride? How many formula units are found in 4.3 moles? If you want to convert it, simply use Avogadro's number. For ionic compounds, the term formula units is used. So 1 mole of aluminum chloride contains 6 times 10 to the 23 formula units. And if we need to convert to, let's say, if we want to find ions of chlorine, we can multiply this by 3. There's 3 chloride ions for every 1 formula unit. So these units cancel and those units cancel. But first, let's find out how many formula units we have. So let's multiply 4.3 times 6. And then afterward, we'll multiply that answer by 3 to see how many ions of chlorine are there. So what's 4.3 times 6 times 10 to the 23rd? So let's multiply these two numbers first. So 4 times 6, we know that's 24. And 6 times 3 is 18, so 6 times 0.3 must be 1.8. And if you add these two numbers, you should get 25.8. So we have 25.8 times 10 to the 23rd. And if we move the decimal 1 unit to the left, you should get 2.58 times 10 to the 24. So that's how many formula units there are in 4.3 moles of aluminum chloride. So now let's find the number of chloride ions. So we know we got to multiply this by 3. So what is 2.58 times 10 to the 24 times 3? So let's multiply these two numbers. 8 times 3 is 24, and so let's put the 2 on the other side. 3 times 5 is 15, add 2, that's 17, and 2 times 3 is 6, add 1, that's 7, so it's 7.74. So we have 7.74 times 10 to the 24 chlorine atoms, or chloride ions, in 4.3 moles of aluminum chloride. Try this one. Let's say if you have 160 grams of sulfur trioxide. How can we convert it directly into atoms of oxygen? So let's create a map, so to speak. We need to convert grams of SO3 into moles. And once we have moles, we can convert it into molecules. And then from there, we can convert it into atoms. So let's begin. Let's start with 160 grams of SO3. And we need to find the molar mass. Sulfur has a molar mass of 32. And for oxygen, it's 16, but times 3. 16 times 3, that's 48. And 32 plus 48 is 80. So the molar mass is 80. So there are 80 grams of sulfur trioxide per 1 mole of SO3. So these units, they cancel. Next, we need to convert from moles to molecules. Now 1 mole of SO3 is equal to 6 times 10 to the 23 molecules, which I'll write as capital M. And now we need to convert molecules into atoms of oxygen. And it turns out that there's 3 atoms of oxygen, so I'll write 3O, for every 1 molecule. So now, let's see if we can figure this out. So what we have on top is 160 times 6 times 10 to the 23rd times 3 divided by 80. So we can cancel a 0, and 16 divided by 8, that's 2. So we have 2 times 6 times 3, and then we have a 10 to the 23rd. Notice I moved the 3 to the front. So 2 times 6 is 12. 12 times 3 is 36. So we have 36 times 10 to the 23rd. And we could take this decimal, move it to the left, and so the answer is 3.6 times 10 to the 24th atoms of oxygen. So now let's try another problem. Let's say if we have 3 times 10 to the 23 atoms of sulfur, and we wish to convert it to grams of sulfur in the form of S8. How can we do that? So feel free to take a minute and see if you can do this problem yourself. So let's start with this. 3 times 10 to the 23 atoms of sulfur. We need to convert it into moles first. So we know that there's 6 times 10 to the 23 atoms per 1 mole of sulfur. Now from here, when we could change the substance, we can convert from atoms of sulfur to molecules of S8, because S8 is a molecule. So we know that 1 molecule of S8 is equal to 8 atoms of sulfur, because 1 molecule has 8 atoms of sulfur. And now we can convert another way we could have done that, let's change it. We're still going to have the 1/8 ratio. So the number is going to be the same. The answer is not going to change. But instead, what we're going to say is that For every 1 mole of sulfur atoms, there are 8 moles. Well, actually, hold on. Let me take that back. We know that there's 8 sulfur atoms per 1 molecule of S8. So for every 8 moles of sulfur atoms, there's 1 mole of S8 molecules. So here we have more like a molar ratio instead, but it's the same. The ratio is still the same. We still have the 1/8 ratio. So instead of saying for every 1 molecule of S8, there's 8 atoms of sulfur, we're saying for every 1 mole of S8, there's 8 moles of sulfur atoms, which is the same. The ratio is the same. So it shouldn't affect our answer. Now the last thing we need to do is we need to convert to grams. So 1 mole of S8 molecules has a molar mass of, sulfur has a molar mass of 32, and then we need to multiply that by 8. Now 30 times 8 is 240, 2 times 8 is 16, 240 plus 16 is 256. So there's 256 grams per 1 mole of S8 molecules. So now we just got to do the math. So let's clear away some space. So the numbers that I had before were 3 times 10 to the 23 on top, and also 256 was on top as well. On the bottom we had 6 times 10 to the 23, and it was an 8. Now we can cancel the 10 to the 23. Now 256, I'm going to write it as 32 times 8, because we multiply 32 and 8 to get to 256 in the beginning. So notice that we can cancel an 8. And 32, I'm going to rewrite it as 32 is basically 2 times 16. And notice that the 3 and the 2, which multiplies to 6, can be canceled with the 6 on the bottom. So our final answer is 16 grams of S8. So what this means is that 16 grams of S8 molecules contain 3 times 10 to the 23 atoms of sulfur, which is what we started with. And so that's the answer for this particular problem. The next topic that we're going to discuss is mass percent, also known as percent composition. If you want to find the mass percent, it's the mass of the element of interest divided by the total mass times 100%. So let's consider methane. So let's say if we want to find the percent of carbon in methane. So the mass percent of carbon is going to be the molar mass, or the atomic mass of carbon, which is 12, divided by the total. The total is 12 plus the atomic weight of the 4 hydrogen atoms, which is going to be 4 times 1, and then times 100%. So 12 plus 4 is 16, so we have 12 over 16 times 100%. Now we can divide the 12 by 4 and the 16 by 4. 12 divided by 4 is 3, 16 divided by 4 is 4. So this is 3/4 of 100%. So how can we figure out this answer as a percentage without a calculator? So 100 is basically 25 times 4. It's 4 quarters. And you can cancel the 4, so basically you need to find out what 3 times 25 is. 3 quarters is 75, so it's 75% carbon. Now mass percent, the mass percent of all the elements must add up to 100. And since there's only 2 elements in methane, the remaining 25% must be from hydrogen. If you take 4, which is the mass of all the hydrogen atoms in CH4, and divide it by the total mass, you get 1/4 of 100, which is 25%. And so that's how you can calculate the mass percent of an element in a compound. Let's try this example. Which of the following compounds contain the greatest percentage of nitrogen? So we got to find the mass percent of nitrogen for each of these choices. So let's start with the first one. So we have the mass of 1 nitrogen atom divided by the total mass for CH5. So we have a carbon, 5 hydrogens, has a mass of 5. 5 times 1 is 5. And the other nitrogen is 14. To save space, we're going to add the 100% later. So 12 plus 14 is 26, plus 5, that's 31. So this is 14 out of 31. Now looking at answer choice B, we only have one nitrogen atom. We have a carbon, which has a mass of 12, 3 hydrogen atoms, so that's 3, plus nitrogen. And oxygen has a mass of 16, but there's 2 of them, so that's going to be 32. Now, 12 plus 3 is 15. 15 plus 14, that's 29. And 32 plus 29, that's 61. So what we have here is 14 out of 61. Whenever you increase the denominator of a fraction, the value of the entire fraction decreases. So therefore, we know that A has a greater percentage of nitrogen than B, so we don't even need to calculate B. So B is out. Now let's move on to answer choice C. Carbon has a mass of 12, but times 2, that's 24. And we have 7 hydrogens, 1 nitrogen. On top, we only have 1 nitrogen atom. So 24 plus 7 is 31, plus 14, that's 45. So here, 45 is greater than 31. So since we have a larger denominator, that means that 14 over 45 is less than 14 over 31. So C is eliminated. Now let's look at answer choice D. So let's make some space. Okay, so we have 3 nitrogen atoms. That's going to be 3 times 14. And on the bottom, we have 6 carbon atoms. That's 6 times 12, plus 5 hydrogen atoms, and the 3 remaining nitrogen atoms. 3 times 14 is 42. 6 times 12, that's 72, plus 5, plus 42. 42 and 72, that's 114. Plus 5, that's 119. So we have 42 over 119. So let's see which of these fractions is greater in value. Let's multiply top and bottom by 3. 14 times 3 is 42, and 31 times 3 is 93. So comparing these two fractions, here we have a larger denominator, which means that this fraction is smaller in value. So therefore, D is eliminated. 42 over 93 is greater than 42 over 119. And so answer choice A is the answer because we have the greatest percentage of nitrogen. And we didn't need to divide these numbers and convert it to a decimal because that's going to take a longer time. Now, if you want to, you could do it that way, but sometimes you got to find the answer quickly. Consider this reaction. Hydrogen gas reacts with nitrogen gas to produce ammonia. Go ahead and balance this reaction. And also, what kind of reaction is it? When hydrogen gas reacts with nitrogen gas to produce ammonia, this is a combination reaction, also known as a synthesis reaction. Whenever you have, let's say, 2 smaller items combining into something larger, it's called a combination or a synthesis reaction. Now, how can we balance this reaction? To balance a reaction, you need to make sure that the number of atoms on the left side is the same as the number of atoms on the right side. On the left side, we have 2 nitrogen atoms, but on the right side, we only have 1. So therefore, what number should we put in front of NH3 to make the number of nitrogen atoms equal? So we got to put a 2 in front of it. But now we have 6 hydrogens on the right side. 2 times 3 is 6. And we only have 2 in front. 6 divided by 2 is 3, so we got to put a 3 in front of H2. And now the reaction is balanced. And there's an invisible 1 in front of N2. On the left side, you have the reactants, and on the right side, you have the product. Now, let's say if we have 5 moles of H2. How many moles of N2 will react with 5 moles of H2? Now, before we answer that question, you need to understand the concept of the molar ratio. Notice that the molar ratio between hydrogen and nitrogen is 3 to 1. So what this means is that 3 moles of hydrogen gas reacts with 1 mole of nitrogen gas. So therefore, 6 moles of hydrogen gas will react with 2 moles of nitrogen gas, and 9 moles of hydrogen gas should react with 3 moles of nitrogen gas. Make sense? It's a 3 to 1 ratio. So therefore, 5 moles, which is somewhere between 3 to 6, should react with how many moles of nitrogen gas? Now, if you want to, you could set up a proportion and you could solve it, but we're going to get the answer using a conversion. So the answer has to be somewhere between 1 to 2 moles of nitrogen gas. But let's find out how much exactly. Since 5 is closer to 6, the number of moles of nitrogen gas should be closer to 2 than it is to 1. So always start with what you have. We want to find out how many moles of nitrogen gas reacts with 5 moles of hydrogen gas. So let's start with 5 moles of H2 and let's convert it. So the molar ratio is 3 to 1, which means that for every 3 moles of hydrogen gas that reacts, 1 mole of nitrogen gas reacts with it. And I put the moles of H2 on the bottom because we have it on top, and I want these 2 units to cancel. So the answer is simply 5 divided by 3. Now 5 divided by 3, we know it's less than 2, but how much is it exactly? So if you want to get a decimal value for it, we need to use long division. So let's put the 5 on the inside, the 3 on the outside. So 3 goes into 5 one time, with 2 remaining. So now let's add a 0. How many times does 3 go into 20? 3 goes into 20 6 times. 3 times 6 is 18, with 2 remaining. And if we add another 0, 3 goes into 20 another 6 times, and we can see that it's going to repeat. So it's going to be 1.6 repeating, which is about 1.67. So 5 moles of hydrogen gas reacts with 1.67 moles of nitrogen gas. That's the answer. So the example that we just considered was a mole-to-mole conversion. But now let's try another mole-to-mole conversion. Consider this reaction. Sulfur trioxide decomposes into sulfur dioxide and oxygen gas, which is O2, in the presence of heat. What kind of reaction is this, and how would you balance it? So notice that this is the reverse of a synthesis or combination reaction. And so this is called a decomposition reaction. So whenever you have, let's say, a large compound, and if you break it into 2 smaller parts, it's a decomposition reaction. Now, how can we balance the reaction? So the number of sulfur atoms are equal, but the number of oxygen atoms are not. Now, we have 3 oxygen atoms on the left side, but we have 4 on the right side. However, if we put a 1/2 in front of O2, the number of oxygens will be equal. There's going to be a 2 in SO2, and a half times 2 is basically 1, so we have 3 oxygens on the right side, 3 on the left. Now, to get rid of the fraction, we could simply multiply everything by 2. And so, if we do that, the 1/2 is going to become 1, and these will be 2. So we have 2 sulfur atoms. 2 times 3 is 6. 2 times 2 is 4. And 1 times 2 is 2. 4 plus 2 is 6. So the number of oxygen atoms are equal on both sides at this point. Now let's say if there are 7 moles of sulfur trioxide, how many moles of oxygen gas will be produced in this reaction? So let's convert it from moles of SO3 to moles of oxygen. So we see that the molar ratio is 2 to 1. So for every 2 moles of SO3 that reacts, 1 mole of O2 will be produced. And so 7 divided by 2 is 3.5. So 3.5 moles of O2 will be produced in this reaction. Consider this reaction. Propane, C3H8, reacts with oxygen gas. What do you think the products are for this reaction? Whenever you have a hydrocarbon, or a molecule that contains carbon and hydrogen, whenever it reacts with air or with oxygen gas, it's going to create carbon dioxide and water. This is called a combustion reaction. Go ahead and balance this combustion reaction. Whenever you're balancing a combustion reaction, balance the carbon atoms first, and then the hydrogen atoms, and save the oxygen atoms for last. So we have 3 carbon atoms on the left side, so let's put a 3 in front of CO2. And notice that we have 8 hydrogens on the left side. So 8 divided by 2 is 4. So let's put a 4 in front of H2O. Now let's add up the number of oxygen atoms that we have on the right side. 3 times 2 is 6. 4 times 1 is 4. 6 plus 4 is 10. And 10 divided by 2 is 5. So we need a 5 in front of O2. And now this reaction is balanced. Now let's say if we put 4 moles of propane with 10 moles of oxygen in a container. How many moles of carbon dioxide will be produced in this reaction? How would you figure that out? When you're given the information for both reactants, and if you want to find out how much product will be produced, you need to take into account the limiting reactant and the excess reactant. Out of those 2 reactants, one of them is limiting and one of them is excess. The limiting reactant is the one that runs out first, and the amount of product that is produced is based on the limiting reactant. So we need to know which one runs out first. A quick way to find out which one runs out first, if you have the moles, is to simply find out which reactant has the lowest mole per coefficient ratio. The coefficient for propane is 1, and for oxygen is 5. So if we divide 4 by 1 and 10 by 5, which number is lower? So 4 over 1 is 4, 10 divided by 5 is 2, so that means that oxygen is the limiting reactant. Even though it has more moles, just because it has more moles doesn't mean it's going to be the excess reactant. The one with the smaller amount of moles is not always the limiting reactant. It's the one that has the lowest mole per coefficient ratio. In this case, it's oxygen, which means that propane is the excess reactant. So using this information, how can we find how many moles of carbon dioxide will be produced? So what we need to do is we need to start with the moles of oxygen, the limiting reactant. The amount of product is always based on the limiting reactant. Don't start with the 2, because that's not the number of moles of oxygen that you have. That's simply the mole per coefficient ratio. So we're going to start with 10 moles of oxygen gas, and let's convert it to moles of CO2. So the molar ratio is 5 to 3. So what this means is that for every 5 moles of oxygen that reacts, 3 moles of carbon dioxide are produced. So now let's do the math. 10 divided by 5 is 2, and 2 times 3 is 6, so the answer is going to be 6 moles of CO2. That is the theoretical yield for this reaction. The theoretical yield is the maximum amount of product that you can get in a reaction. And a theoretical yield could be in units of moles, or it can be units of grams, but grams is more common. Now let's say if we carried out the experiment and it turns out that out of the 6 moles of carbon dioxide that we can possibly get, let's say we only get 5 moles of CO2. If we actually got 6 moles of CO2, that means that the reaction was 100% efficient. Everything was perfect, but in reality that doesn't happen. So this is the most that we can get from this reaction. But if we actually got 5 moles of CO2, this is called the actual yield. That's how much we actually got in the experiment. And the maximum amount that we can get is known as the theoretical yield. So if we only got 5 moles of CO2 out of a maximum of 6 moles of CO2, what is the percent yield? Percent yield is defined as the actual yield divided by the theoretical yield times 100%. So in this experiment, or in this reaction, the actual yield was 5 moles. The theoretical yield was 6. So we need to convert 5 over 6 into a decimal. So let's use long division. How many times does, actually, it should be like this. I had it backwards. Well, 6 can't go into 5, so we need to add a 0. How many times does 6 go into 50? We know 6 times 7 is 42, 6 times 8 is 48, 6 times 9 is 54. That's too much. So 6 can go into 50 at least 8 times. And 6 times 8 is 48. And so we're going to have a 2 remaining. And let's put a 0. So how many times does 6 go into 20? 6 go into 20 at least 3 times. And so 6 times 3 is 18. 20 minus 18 is 2. So this is going to keep on going forever. So 0.83 is enough. So 5 over 6 is about 0.83. And if we multiply by 100%, the answer is about 83%. So that is the percent yield for this reaction. Now, what do you think the percent error is? Percent error is equal to the theoretical value minus the actual value divided by the theoretical times 100%. Sometimes it could be described as the theoretical minus the experimental divided by the theoretical. So the theoretical is 6, the actual is 5, and the theoretical on the bottom is 6 as well. So 6 minus 5 is 1, so this is 1/6. So how many times does 6 go into 1? We need to add a 0. Now we need a decimal because 6 can't go into 1. Now 6 goes into 10 one time. And 1 times 6 is 6, so, and 10 minus 6 is 4. If we add a 0, we'll get 40. 6 goes into 40 at least 6 times. And that's going to be 36. So 40 minus 36 is 4. If we add a 0, we'll get another 40, so it's going to keep repeating. So 1/6 is about 0.16 repeating, or if we round it, 0.167. So if we multiply that by 100, you simply need to move the decimal 2 units to the right. So 0.167 times 100% is 16.7%. That is the percent error. Notice that the percent yield and the percent error adds up to 100%. The percent yield, if we round it to a whole number, it's about 83%. And the percent error, if we round that to a whole number, it was 16.7. So we can round that to 17%. It adds up to 100. So if the percent yield is 20%, the percent error is 80%. If the percent yield is 7%, the percent error is 30%. These two have to add to 100. So now let's go back to our reaction. C3H8 plus O2, and that turns into CO2 and water. And this was 1, this was 3, that was 4, and this was 5. And we had 4 moles of propane and 10 moles of oxygen. Now we said that oxygen was the limiting reactant, which means that propane is the excess reactant. So let's say if this reaction is complete, and let's say that percent yield is 100%. How many moles of the excess reactant remains? Now, the first thing you need to do is find out how much of the excess reactant actually reacts. And then you can subtract the total amount of the excess reactant that was there to begin with, minus the amount that reacts, and that's how you can get the amount that's left over. Now, to find the amount that reacts, you need to use stoichiometry. You need to convert. You need to find the stoichiometric relationship between oxygen and propane. So here's what you need to ask yourself. How many moles of propane reacts with all of the 10 moles of oxygen gas? So basically, take the limiting reactant, which is 10 moles of O2, and convert it to the moles of propane. So using the molar ratio of 1 and 5, for every 5 moles of oxygen that reacts, 1 mole of propane is going to react with it. So these will cancel, and 10 divided by 5 is simply 2, so the answer is 2 moles of propane. Now, what does this number mean? You need to understand what it means. So what it means is that 10 moles of oxygen reacts with 2 moles of propane. So this is the amount that reacts, or the amount that is consumed by the reaction. So if we started with a total of 4 moles, or this is how much we had at the beginning, the initial amount, and if we subtract it by the amount that reacts, then the amount that's left over is the difference between 4 and 2, which turns out it's 2 as well. So this is the amount that remains. And so 2 moles of propane remains after the reaction is complete. And that's how you can find the amount of the excess reactant that remains. So now let's try a different example. Butane, C4H10, reacts with oxygen gas to produce carbon dioxide and water. Now, pause the video and go ahead and balance this reaction. Now keep in mind, whenever you want to balance a combustion reaction, balance the carbon atoms first, then the hydrogens, and save the oxygen atoms for last. So we have 4 carbon atoms on the left side, so we need to put a 4 in front of CO2. And there's 10 hydrogens on the left side, so we need to put a 5 in front of H2O. Now right now we have 4 times 2, which is 8 oxygen atoms, and 5 times 1, that's 5 oxygen. So if we add these two, that's 13 on the right side, which means we need 13 on the left side. 13 divided by 2 is, well, 13 over 2. So now the reaction is balanced, but used in fractions. So we need to multiply everything by 2 to get rid of the fractions. So this is going to be 8, that's going to be 10, this is going to be 13, and this is going to be 2. So we have 8 carbon atoms on both sides, 20 hydrogen atoms, and here we have 16 oxygen atoms, and here 10 times 1, that's 10, and 13 times 2 is 26. So, and 10 plus 16 is 26, so the number of oxygen atoms are also equal on both sides. So now let's say that there are 7 moles of butane and it reacts with excess oxygen gas. So that's the excess reactant, which means that this must be the limiting reactant. How many grams of carbon dioxide are produced in this reaction? So we want to convert from moles of butane to grams of carbon dioxide. How can we do that? Well, let's start with moles of butane. Now, whenever you want to change from one substance, in this case butane, to another substance, like CO2, you need to use a molar ratio. In this case, it's 2 to 8. So for every 2 moles of butane that reacts, 8 moles of carbon dioxide will be produced. So now, we need to convert moles of CO2 into grams of CO2. So whenever you want to go from moles to grams, you need the molar mass. Carbon has a molar mass of 12, and for oxygen is 16, but times 2. 16 times 2 is 32, plus 12, that's 44. So there are 44 grams of CO2 per 1 mole of CO2. So these units cancel, and those units cancel as well. So we can divide 2 into 8. We should get 4. And 4 times 44, well, 4 times 40, that's 160. And 4 times 4 is 16, so 4 times 44 is going to be 160 plus 16, that's 176. And then we need to multiply 176 by 7. So let's make space here. So 176 times 7. 6 times 7 is 42. And 7 times 7 is 49. Plus the 4, that's going to be 53. 7 times 1 is 7. Plus 5, that's 12. So 176 times 7 is 1,232. Let's confirm that answer with the calculator. And that is correct. So that's the number of grams of CO2 that can be formed in this reaction. Now keep in mind, this represents the maximum amount of CO2 that we can get from this reaction based on the 7 moles of butane that we started with. So basically, this represents the theoretical yield of CO2. Now, let's say if the question also mentioned that this reaction is 80% efficient, and if that's the case, how many grams of carbon dioxide should we expect to collect from this reaction? So if they mention it was 80% efficient, you would still need to find the theoretical yield, which is 1232. But to find out how much you would actually collect, which is basically the actual yield, you need to find out what 80% of this value is. So we said that percent yield is equal to actual divided by theoretical times 100. So if you want to solve for the theoretical, for the actual yield, it's going to be the percentage divided by 100 times the theoretical yield, and that's going to equal the actual yield. The percentage is 80%. We said the process is 80% efficient, and we're going to divide that by 100%, and we're going to multiply by the theoretical yield, which is 1232. 80 divided by 100 is basically 0.8. So we're looking for 80% of 1232. So what is 80% of 1232? How can we figure this out? So how can we figure out 80% of 1232? Let's see. What's 10% of 1232? 10% is 123.2. So if that's the case, how much is 20%? 20% has to be twice the value, so that's 246.4. If we take away 20% of 1232, we're going to have 80% left over. So 1232 minus 246.4, that's going to give us 80% of 1232. And 246.4 is basically 100 or 232 plus 14.4. Now 1232 minus 232 is 1,000. And 1,000 minus 14, that's 986. And if you subtract 986 by 0.4, you should get 985.6. And if you take your calculator, if you type in 1232 times 0.8, you should get the same thing, 985.6. So what I'm doing is I'm showing you different techniques in which you can calculate the answer, hopefully mentally as well. You want to get to a point where you can do these calculations mentally, and it's going to save you time, and it's going to help you a lot if you can't use a calculator. But sometimes it makes sense to write it by hand. You can always fall back to this method. So you just got to find out which method is more suitable to you, which one will help you to get the answer quickly and at the same time accurately. You don't want to make mistakes as you do your work. Let's try this problem. 24 grams of ethanol is placed in a container with 53 grams of oxygen gas. 21 grams of carbon dioxide are collected in this reaction. What is the percent yield of CO2, and how many grams of excess reactant remains at the end of this reaction? In order to find the percent yield, we need to calculate the theoretical yield. And notice that the actual yield was given to us. It's 21 grams of CO2. Now notice that we have the grams of both reactants, ethanol and oxygen gas, which means we need to know which one is limited and which one is excess. Now we're going to find the limited reactant using a different technique than what we did before. In the other example, we found which reactant had the lowest mole per coefficient ratio. And that technique was suitable because we already had the reactants in moles. Now for this one, we're going to find the limiting reactant by taking the grams of each reactant and doing a gram-to-gram conversion, or stoichiometry. We're going to convert the grams of each reactant to the grams of CO2, which is the theoretical yield. The reactant that gives us the lower theoretical yield, that is the limited reactant. And the smaller of the two theoretical yields would be the correct theoretical yield. And once we have that, we can find the percent yield. So let's go ahead and begin. So let's write a balanced reaction. So we have C2H5OH. It reacts with oxygen gas, and since it's a combustion reaction, we're going to get CO2 and water. Now the first thing you want to do is balance the carbon atoms. So notice that we have 2 carbon atoms on the left side. So we need to put a 2 in front of CO2. And notice that there's 6 hydrogens, 5 plus 1, on the left side. So 6 divided by 2 is 3, so let's put a 3 in front of H2O. Now let's count the number of oxygen atoms on the right side. Notice that we have 4 oxygen atoms from the 2 CO2 molecules and 3 oxygen atoms from the water molecules, so we have a total of 7 oxygen atoms. But we already have 1 from ethanol, which means we need 6 from O2, because 1 plus 6 equals 7, and 6 divided by 2 is 3. And so now the reaction is it's balanced. By the way, the video that you're currently watching is simply the first 3-hour trailer version of a longer 8.5-hour video. So I'm going to post a link to the rest of the video, the remaining part, and you can check that out if you want to. And so here it is, and let's continue on with our next concept. So what we're going to do now is called a gram-to-gram conversion, or gram-to-gram stoichiometry. We're going to start with 24 grams of C2H5OH, and we're going to convert it to grams of CO2. So first, we're going to convert grams of C2H5OH into moles using the molar mass, and then we're going to convert the moles of C2H5OH into moles of CO2 using the molar ratio, which is found in a balanced reaction. And then once we have moles of CO2, we're going to convert that back to grams using the molar mass of CO2. And that's how you can do a gram-to-gram conversion. So let's start with 24 grams of C2H5OH. Now for these longer conversion problems, it's good that you write all 3 parts of this conversion process: the number, the unit, and the substance. The number is the 24, the unit is the grams, the substance is C2H5OH. And if you write all 3, it's going to help you to avoid making mistakes. So let's convert grams into moles. So we need to use the molar mass. So the molar mass of C2H5OH, we know carbon is 12, there's 2 of them, so that's 24. There's 6 hydrogens, so that's plus 6, that's 30. And oxygen is 16, 30 plus 16 is 46, so the molar mass is 46. So there's 46 grams of C2H5OH per 1 mole of C2H5OH. So these units cancel. Now, we need to use the molar ratio to change the substance. So notice that it's a 1:2 ratio. So for every mole of C2H5OH that reacts, 2 moles of CO2 are produced. So now we need to convert moles of CO2 into grams. And the molar mass of CO2 is, well, we know carbon is 12, oxygen is 16 times 2. So that's 32 plus 12, that's 44. And so for every 1 mole of carbon dioxide, there are 44 grams of CO2. So now, we need to figure out what the answer is. So 46 divided by 2 is about 23. And 24 over 23, that's very close to 1. it's a little bit more than 1. So 1 times 44 is 44, but because it's a little bit more than 1, let's say the answer is approximately 45. Now, let's actually use the calculator to see what the answer is, but sometimes you may have to estimate it if you don't have a calculator. So our estimate is 45. 24 divided by 23 times 44. The actual answer is 45.9 grams. So let's add 0.9. Now, let's calculate how many grams of CO2 can be produced from the 53 grams of oxygen. The number that we have, the 45.9, that's how many grams of carbon dioxide that can be produced if all of the 24 grams of ethanol reacts. But now we need to know how many grams of CO2 can be produced if all of the 53 grams of oxygen reacts. So what I want you to do is pause the video and start with 53 grams of O2 and convert it to the grams of CO2 using the same 4 steps that we have on the board. And you may have to modify some of those steps, but follow the same generic process to get the grams of CO2 that can be made from 53 grams of O2. So starting with 53 grams of O2 over 1, let's convert it to moles. The molar mass for oxygen is 16, so for O2 it's going to be 32 grams. Now, we need to use the molar ratio to convert from O2 to CO2, so it's a 3:2 ratio. So for every 3 moles of O2 that reacts, 2 moles of carbon dioxide are produced. And the last part, converting moles of CO2 into grams, we already have the molar mass of CO2. It's already 44, so we don't need to recalculate it. So now we got to do some math. So we have 53 times 2, and 44 is basically 11 times 4. And we have a 3 on the bottom. 32 is 8 times 4. And the 8, I can break it into 2 and 4. So 4 times 2 times 4 is 32. The 4's cancel and the 2's cancel. So it makes our job a little bit easier. So what we have is 53 times 11 over 12. So 11 over 12 is just under 1. So the answer should be less than 53, but not too far away. It could be close to 50. But I think it's more than 45.9, which means this is the correct theoretical yield. Now the actual answer for this, it's 48.6 if you use a calculator. So because this number is smaller, 45.9 is the correct theoretical yield. Now the reactant that gave us the correct theoretical yield is the limiting reactant. So ethanol is the limiting reactant and O2 is the excess reactant, because oxygen gave us a greater theoretical yield. And so that's why it's the excess reactant. So that's how you can find the theoretical yield if you're given the grams of both reactants. Simply take the grams of each reactant and convert it to the grams of product, and whichever gives you the lower number, that is the correct theoretical yield. And by doing that, you'll know which one is the limiting reactant and which one is the excess reactant. So now that we know which one is the theoretical yield, we can calculate the percent yield. So the percent yield is going to be the actual yield, which is 21, divided by the theoretical yield, which is 45.9 times 100%. So let's round that to 21 over 46. So 23 over 46, that's like 50%. So this is under 50%. This could be like somewhere between 40 and 50% if we have to estimate it. So 46 into 21. Let's add a 0. So we have 46, 92. Let's see, 46 plus 92, that's 138. If we add 46 again, that's going to be 184. And if we add another 46, that's 230. So 230 is too much. So 46 goes into 210 at least 4 times. And 210 minus 184, that's 26. And if we add a 0, that's 260. If you add 46 to 230, that's 276. So 46 goes into 260 5 times. 46 times 5 is 230. And at this point, I'm out of space, so I'm going to go with 0.45. We said it was between 40 and 50%, so I'm going to say roughly around 45%. Now, using the calculator, the actual answer, which is 21 over 45.9 times 100, it's about 45.8%. But this is a very close approximation if we can't use the calculator. Now, if I had more space, I could get a more accurate answer, but I ran out of space. But you know what to do from this point. So now let's focus on the second part of the problem. So, how many grams of excess reactant remains at the end of this reaction? We said oxygen is the excess reactant, and we have an initial amount of 53. We need to find out how many grams of oxygen gas reacts with the 24 grams of ethanol. Once we get that answer, we're going to take the total amount of oxygen, which is 53, minus the amount that reacts to get the amount that's left over. So in order to find the amount that reacts, let's start with 24 grams of ethanol. And we need to do another gram-to-gram conversion. And we know the molar mass of ethanol is about 46 grams. So at this point, we need to convert the substance. We need to change from ethanol to O2, and the molar ratio is 1 to 3. So for every 1 mole of C2H5OH that reacts, 3 moles of oxygen reacts with it. And the last thing we need to do is convert moles of O2 into grams, and the molar mass for O2 is 32. So now we have some math to work with. So we have 24 times 3, 46 is 23 times 2, and 32 is 16 times 2. So we could at least cancel the 2's. So now we got to do some more math. Now, 16 times 3 is about 48. And let's see. If I round 24 down to 23, I'm going to increase 48 to about 50. So 24 over 23 is about 1. Since I decreased the 24 to 23, I got to increase the 48 up to a higher number. So I'm going to say the answer is about 50. Using the calculator, 24 times 3 times 16 divided by 23, the actual answer is 50.09. So 50 was a good estimation. Now, 48 was twice the value of 24. So when I decreased 24 to 23, if I decreased 24 by 1, I had to increase 48 by 2 because 48 is twice the value of 24. And the answer was pretty accurate when I did that. Now, we don't have the final answer yet. The 50 is the amount of oxygen that actually reacts in this reaction. So the amount that's left over is the difference between 53 and 50. So we have 53 grams of oxygen gas to begin with. And out of the 53, only 50 grams react. So the amount that's left over is 53 minus 50, which is 3 grams of oxygen. And this is the amount of the excess reactant that remains at the end of this reaction. So that's the final answer to the second part of this problem. Now let's try this one. So a compound contains 20 grams of carbon, 3.3 grams of hydrogen, and 26.7 grams of oxygen. What is the empirical formula? So how can we find the empirical formula of a compound? Well, what you need to do is convert the grams into moles for every element. And then once you have the moles, divide it by the smallest of the 3 moles that you have. And then using those numbers that you have, you can write the compound. So let me give an example. Let's start with 20 grams of carbon. And let's convert it into moles. So carbon has a molar mass of 12. Now for this example, I'm going to use a calculator. Sometimes I will use a calculator, other times I will try to simplify it without the use of a calculator. So you can boost your math skills. 20 divided by 12 is about 1.67. And for hydrogen, which has a molar mass of about 1, it's going to be 3.33 for hydrogen. Now for oxygen, the molar mass is not going to be 32 because we don't have oxygen gas. We have atomic oxygen that's in the compound, so we need to use a molar mass of 16. And so 26.7 divided by 16 is about 1.67. Now what we need to do at this point is divide each of these numbers by the smallest of the 3. The smallest is 1.67. So this is going to equal 1, this is 2, and that's 1. So this was for carbon, hydrogen, and oxygen. So the formula is going to be C1H2O1, or simply CH2O. And that's how you can find the empirical formula of a compound. So now that we have the empirical formula, how can we find the molecular formula if we have the molar mass? Now the molar mass for the molecular formula is 180. So what we need to do is find the molar mass of the empirical formula. Carbon is 12, plus the 2 hydrogens, which is 2, that's 14, plus oxygen, which is 16. 14 plus 16 is 30. So what you need to do is divide these two numbers. 180 divided by 30 is the same as 18 over 3, which is 6. So because the molar mass of the compound is 6 times more, we need to multiply the subscripts by 6. So C1H2O1 is going to become C6H12O6. And so this is the molecular formula, and this is the empirical formula. The empirical formula is the lowest ratio possible of any molecular formula. And you have to use whole number ratios if you want to write the empirical formula. So let's say if we have the formula C4H18O8, the empirical formula would be C2H9O4. We can divide each of these numbers by 2. So the empirical formula is simply the lowest whole number ratio of any molecular formula. Now, sometimes you might have the percent composition of a hydrocarbon, and you may need to find the empirical formula. So let's say a hydrocarbon, which consists only of carbon and hydrogen, has a mass percent of 88.2 for carbon, and the mass percent for hydrogen is 11.8%. So in the last example, we were given the grams of the elements. Now we're given the mass percent or percent composition. If you're given the percent, simply base it out of 100 and just convert the percent into grams. So this means that we have 88.2 grams of carbon and 11.8 grams of hydrogen. Because the total is 100 grams. 88.2 grams of carbon out of a total of 100 grams of the substance, that's still 88.2%, and that's why it works. So now let's convert the grams of each substance into moles, and we're going to use a calculator for this. And let's do the same for hydrogen as well. This is supposed to be 1 gram of hydrogen. So 88.2 divided by 12, that's 7.35, and the other one's going to be 11.8. So we need to divide these two numbers by the smaller of the two. So this is going to give us 1 for carbon, and 11.8 divided by 7.35, that's about 1.6. So we don't have a whole number here, so what should we do? So for carbon, it's 1, and for hydrogen, it's 1.6. So if we write the formula, it's C1H1.6. Now, 1.6 over 1, if we multiply the top and the bottom by 10, this is the same as 16 over 10. And then see if you can reduce the fraction. If we divide by 2, this is 8 over 5. So what I'm going to do is multiply the subscripts by 5. 1 times 5 is 5, so it's C5. And 1.6 times 5, if you type that in your calculator, you're going to get 8. So this is going to be H8. So 8 over 5 has the same ratio as 1.6 to 1. So the 1.6 corresponds to the hydrogen, and so does the 8. The 1 corresponds to the carbon, and so does the 5. And so if you get a decimal whenever you're dealing with the empirical formula, convert it into a fraction, and then multiply top and bottom by 10 until you get just whole numbers and reduce the fraction. And that's how you can find the empirical formula. A 4.532 gram compound consisting only of carbon and hydrogen produced 13.851 grams of CO2 and that many grams of water during combustion analysis. Determine the empirical formula of this compound. So how would you do this problem? Now, what we need to do is find the moles of carbon and hydrogen. If we can do that, then we can find the empirical formula. So let's begin. So notice that we have 13.851 grams of CO2. And we know that the molar mass of CO2 is about 44. Now, we need to convert the moles of CO2 into moles of carbon. Notice that there's one carbon atom in one molecule of CO2, so the molar ratio is 1 to 1. So for every mole of CO2, there's 1 mole of carbon atoms. So 13.851 divided by 44, that's going to be 0.315 or 0.3148 moles of carbon. Now let's do the same thing for water. We have 6.798 grams of H2O, and the molar mass of water is 2 plus 16, so it's about 18 grams per 1 mole. Now we need to find the moles of hydrogen, and notice that there's 2 atoms of hydrogen in a single molecule of water. So for every 1 mole of H2O, there's 2 moles of hydrogen atoms. It's a 1 to 2 ratio. And so these units cancel, and those units cancel. So 6.798 divided by 18 times 2, this is about 0.7553 for hydrogen, and this is for carbon. So let's divide these two numbers by the smallest. So we're going to divide this number by 0.3148, and this one by also by 0.3148. So for carbon, it's going to be 1, and for hydrogen, it's 0.7553 divided by 0.3148, which is about 2.4. So, using this information, how can we get the empirical formula? So let's divide 2.4 by 1. So keep in mind, for hydrogen, hydrogen is associated with 2.4, so hydrogen is associated with the number on top, and carbon is associated with the number on the bottom. So what we're going to do now is multiply the top and the bottom by 10. So it's going to be 24 over 10. So we can reduce this fraction if we divide both by 2 because both numbers are even. So half of 24 is 12, half of 10 is 5. So now it's going to be C5H12, and that's the empirical formula for this problem. So we really didn't need to know the mass of the compound. If we knew the mass of carbon dioxide and water that came from it, we can calculate the moles of carbon and the moles of hydrogen that came from the compound. And so that's it for this problem. Because keep in mind, when you have a combustion reaction, all of the carbon and the hydrogen comes from the compound. So if you could find the moles of carbon and the moles of hydrogen, then you can find the empirical formula.